Hello everyone and welcome to this course on design patterns in Kotlin. In this first video, I want to give you a brief overview of what you can expect when you are taking this course. And I want to go into a bit of detail about what design patterns are and why we might want to use them. So first of all, this course goes through a number of design patterns that are useful when you are developing in Kotlin. So obviously, if you've used Kotlin for your Android development needs, then you might be familiar with the development process. So you would know how to build your programs in Kotlin, but there is a whole other level that you might not be familiar with, and that is the world of design patterns. So basically, what are design patterns? Design patterns are a way to solve similar problems in similar ways. Okay, so obviously we're not trying to reinvent the wheel every time we are building a application or a piece of code. What we want is to be able to solve certain problems in a way that we know is successful and we know is scalable. Okay, so that will allow us to not run into some issues later on. So there are certain situations where you might find it really useful, or you might recognize a certain problem. It's very useful to know how to solve that problem in a correct way. Okay, so we're not trying to reinvent the wheel. We know that everything has already been done. The only issue is if we want to build scalable, robust programs, we need to understand how to solve various problems that occur, and we need to be able to recognize those problems when they happen. Design patterns also introduce a standard terminology. Okay, so it's much easier to say that you've used a builder pattern, okay, and the person you're talking to will immediately understand what you mean by that, rather than explain to them that you have built a constructor in a certain way and you have certain functions that do a certain functionality, right? So it introduces a standard terminology that you can use to describe how you've solved a certain problem. It also introduces best practices. So like I mentioned, you want to be able to solve problems that you already saw before. Okay, you don't want to spend too much time figuring out a solution to a problem when that problem has already been solved and there is a very good solution for that, or I would say correct solution. Okay, because some solutions will give you problems later on if they are not implemented correctly. Okay, so when your application or program scales, you need to introduce more functionality and more parts of your code, then your solution might break if it's not built in the correct way. Okay, so that's what best practices are a way for design patterns to help us solve problems that are quite common in a very specific way. Now, the Gang of Four represents a group of four architects, okay, software development architects, that have released a book that provides the solution to a lot of problems. Okay, so these are the design patterns. That's why they are called them patterns. So the Gang of Four represents a kind of high-level overview of how you would solve certain issues in your code. In this course, I am taking the most common design patterns in the Gang of Four book and applying them in our Kotlin development with specifically Android development focus. Okay, so we are going to be looking at how we apply the design patterns given to us by the Gang of Four, which is considered kind of the Bible in this particular topic, the foundation book. We will see how we apply those design patterns to our Kotlin development needs. All right, guys, so that is the overview of this course. You're going to get the knowledge to recognize problems that have already been solved and apply the solution that was described in the design pattern problem solving. Okay, so we're going to have a look at that. In the next video, we're going to have a look at what types of design patterns there are and what they are useful for in general. I will see you in the next video. All right, so in this video, we're going to talk briefly about the types of design patterns that we have. So mainly we have three types of design patterns. The first type is the creational design pattern. The creational design patterns usually handle object creation. Okay, so how do you instantiate an object from a class? How do you provide all the variables and functionality that object needs in order to be created? Okay, there are a few different problems, common problems in this area, and we will see different solutions to these problems and when to apply those. Next up, we have the structural design patterns. So the structural patterns relate to how various objects and components in your applications relate to each other. Okay, how do you structure your code in such a way as to not only solve the problem that you have at hand in an easy way, okay, but also achieve various good to have objectives, right? Such as separation of concerns, such as scalability, testability, and so on and so on. So that is what the structural design patterns do. They show you how you can structure your code in such a way to achieve some higher level objectives. And then finally, we have behavioral patterns. So behavioral patterns relate more to how your object function inside your code. Okay, so how your strategy will affect the structure of your application, how objects communicate, how they relate to each other, and so on and so on. So these are the behavioral patterns, and we have quite a few of these because they are quite useful in various situations. Now, you also have a fourth type of design pattern, and that is the concurrency design pattern. We're not going to cover those design patterns in this project because it kind of exceeds the scope. And also I have covered these design patterns in my course on Kotlin coroutines. So have a look at that if you're interested. In this course, we're going to cover the three main types and the most common design patterns that there are. And these are the creational, structural, and behavioral patterns. All right, so let's get started. In this video, we're going to set up our project and we're going to run a quick test to see that our project is well set up. So first of all, I am using here, for the purposes of this course, I'm using the IntelliJ IDEA. You can see it here, right? The reason why I'm using this is because it will allow us to easily run Kotlin code, test out new functionality. It has a really quick turnaround time. Okay, you could in principle use Android Studio if you want to use that, but that comes with a lot of overhead and the whole Android ecosystem, right? So this is for me personally, I think this is better for testing Kotlin code directly, right, without running through Android. All right, so if you don't have this already installed, just go to Google and do a quick search for IntelliJ IDEA. The first result that pops up is the website. This is completely free. It comes bundled with Kotlin by default, so it's really a good way to run your Kotlin code. All right, so once you are at this stage, let's go ahead and create a new project. And here is where it's quite important what options we select. So for our project, we will need to add some dependencies, okay? So that means we need to select the Gradle. Gradle is obviously a build tool, okay? So build configuration, so Gradle and Kotlin/JVM, okay? That's the one we need. We don't necessarily need Java. We don't need simple Kotlin. We need Gradle, Kotlin, JVM, okay? Next up, you can give it whatever name you like. That doesn't really matter. I'm gonna say Kotlin design patterns. Okay, so let's finish up. And I'm just gonna wait for the project to be built. This shouldn't really take long because we don't really have too much in our project. We just have a Gradle configuration. All right, so that's all there is to it. Now, in Gradle here, we need to add a couple of dependencies, right? So here we have our test implementation. And here we have org.junit.jupyter :junit -Jupyter -API 5.3.2. And we have another test implementation that's going to be org.assertj :assertj -core 3.11.1. All right, so why do we need test implementation? Well, the way we're going to use this functionality, the way we're going to build our code is we're going to build a class that exemplifies our design pattern, and we're going to use the JUnit functionality to create some unit tests for our class to run, okay, to make sure that everything is as we are expecting. So that means we need a test implementation because the code we're going to be building is in the test folder. Okay, we need JUnit for obviously unit testing, and we need AssertJ for the assertions that we're going to put in place. So things like, is this object equal to this object? Is this value greater than, smaller than this value, and so on. Okay, so these are the assertions. Let's go ahead and build our project or rebuild our project. Okay, that looks fine. If there's an error here, it means you made a mistake typing this, so make sure everything is correct. All right, now, since all of this is set up, I want to make sure that it runs correctly, right? So let's go ahead and create here a test class to create a test and run it, okay? So inside our source folder, inside test, inside Kotlin, I'm going to right click, create a new Kotlin file, and here I'm going to say something like, let's say calculator. The reason for that is I'm going to create a simple class that just has a function a plus b, and we're going to run a test to make sure that that function works correctly. The point is obviously to make sure the tests run rather than create a correct class. Okay, so inside our calculator class, I'm going to create a fun sum a of type int, a b of type int, and that returns a plus b. Okay, so that's our simple class. Now let's go ahead and create a test class. So calculator test. Okay, so inside here we have a function test sum. Okay, we're going to annotate this with @test. Okay, let's make sure that we need to apparently add testing to class. Let's have a look if that solves our problem. I think JUnit, we need to add JUnit. So let's go ahead and import. JUnit is the one that we need. Okay, so we have our JUnit. Let's have a look here. I don't think we need the test ng. This is JUnit Jupyter. These two, let's leave them both. I think they should be fine. So now we are in test sum. Let's go ahead and create our assertions. Make sure you select the AssertJ one here. Dot assert that. Let's create a val calc is going to be a calculator object, and we're going to say calc.sum of 3 and 5 dot, so assert that. I think I've made a small mistake here for the int. Okay, there we go. So assert that is equal to 8. Okay, so that should give us a good result. Let's go ahead and right click and then select run. Okay, so this I was kind of expecting. If you get this error, test events were not received, then you need to do the following. If your test runs, then you are good to go. If you get this, then you need to go to preferences. Okay, go to build execution deployment. Let's have a look. Build tools, Gradle, and here for the test, run test using, here select IntelliJ IDEA. Okay, click OK. That should be fine. Let the system, think about it for a minute or so. And then I'm going to do the same thing, right click, run test. And then that is all there is to it. Okay, so our tests run, and from now on we can start to create our files here and run them using the tests similarly to how we've done for this calculator test. All right, so let's get started with the first of our creational patterns, which is the singleton pattern. The singleton pattern is quite simple, and maybe you've heard of it, maybe you've used it in the past. So let's go through a small example of why, or a situation where you might want to use singleton. Okay, so let's assume you have a few components in your application that are trying to access some external environment, some external utility, right? Let's say a network communication. Now, each of these components could, in principle, instantiate its own network communication, okay, and then communicate with the web in the way they need to, right? Now, this is problematic for a few different reasons, right? So you might have a problem in the network communication where you could have multiple of these network communication instances communicate in different ways, or you might have delays, or you might want to order your communication in some way, right? So you can't really do this with this particular architecture. So in that case, what we ideally would like to have is a single instance of our network communication service, let's say, that all other components communicate with, and all requests for the network go through that network communication instance, okay? So that you can do some, let's say, ordering, some logging, some, there's a lot of things that you could do with a single one that you can't do with multiple. So basically, you only have one instance. That's the main idea of a singleton. Only one instance of a certain service or a certain component in your application. So it's a single point of access for a resource. So you can think about, for example, a database where you would want a single point of access, so a database, a network communication service, or you could want, let's say, a logging service or things like that, right? Now, so these are a few examples: utility classes, database access. There's a whole list of examples. Now, keep in mind that the list is quite limited, so there's not an infinity of these resources. Singleton is only useful when you require a single access to your resource. And it might also be a disadvantage in some situations, right? So for instance, if you create a singleton, that singleton instance will remain created and will take up resources for the remainder of your application. Okay, so you might not want that, especially in a environment with a limited set of resources like a mobile device, right? So do use it if you need to, but be careful not to overuse this this design pattern. So how would you go about creating it in Kotlin? Well, Kotlin has a very simple way of creating it. So here I'm going to show you the kind of Java way to create a singleton. And then I'm going to show you how Kotlin makes it really, really easy for us to create this, this system, this singleton design pattern. So in the Java way, you would basically create a holder variable or a holder instance that is made private. You would make a private constructor so that you cannot create new instances of this particular class. And then you create a static functionality that allows you to create the singleton itself, right? So this is the classic Java way of creating a singleton. Now, how would you do that in Kotlin? Well, it's much, much easier. You simply create what we call an object of the class singleton, okay? So the object is a simple singleton. It only allows you to make one instance of this particular class. Very, very simple, very basic. So let's have a look at code. Let's see how we can put in practice this this design pattern. So let's go ahead and create a new Kotlin file, and I'm going to call this, let's create a network access device, right? So network driver. Okay, I'm going to make a class here. So first of all, I'm going to make a class, show you how we instantiate, print out the instance, make sure it's different, and then we create an object and do the same thing to kind of see the difference there. So I'm going to create an init block, print line. Here I'm going to say initializing with, or initializing this. Okay. And here I'm having a fun print line or print, let's say, or we could say log. Okay, that returns a network driver. And let's say apply print line network driver $this. And let me just correct that, network, and instead of applying, we're just going to simply return that apply, so that we do get a return network driver here. All right, so let's create a test class. So I'm going to say class singleton test, and I'm going to create a test function fun test singleton. Print line, let's print a start here so that we see the start point. Then we're going to create a couple of objects. So let's call this network driver 1 is going to be network driver dot print dot log, and then val network driver 2 is going to be network driver dot log. Okay, so these two should print out the message. We're not going to do any checking for now because we still have a class that is not a singleton. So let's go ahead and run this. And we should simply see initializing and network driver. We should see the output of that. There we go. So we have one object and we have our second object. Now let's convert this to an object. Okay. And then if we convert it to an object, we don't need the instantiation here. Okay, so no parentheses. So that is that. Now let's go ahead and assert that, or let's say assertions from assertj dot assert that. And I'm going to say network driver 1 driver 1 is same as, so the same object as network driver, and then assertions dot assert that network driver 2 is the same as network driver. Okay, so we're making sure that what we are getting here is the same as the actual object here. Okay, so let's go ahead and run the test case. There we go. So we are getting test result initializing. So we're initializing the actual object. Okay, you can see that we are initializing only once, whereas before we are initializing for each object. Here we are getting network driver same ID and same ID. Okay, we have two logs but the same object, so that is a singleton, and we are asserting here that it is actually the same as the object here. Okay, that test has passed. So very, very simple. The only thing that you need to do in Kotlin to create a singleton is pass this or create an object rather than a class. All right, so let's talk about the factory method. As the name suggests, factory refers to something that creates something else, some product, right? In our specific case for Kotlin development, here we use the factory method to provide some functionality or some instantiation for the calling elements. Okay, so let me just explain what that means. So first of all, let's assume we have a type of currency, right? This can be an interface or an abstract class. And here we have a few instantiations of that concept. Now, if we want to create a country that implements a specific currency, then that particular country needs to know what kind of currency it needs, right? So the object country, when it is created, needs to know how to create the object currency. Okay, so it needs to have all the details of the lower level implementation, right? Now, what we want to do is ideally we would like to abstract the implementation of currency from the country. They are two separate entities, and there's no reason for them to, for the country to know how to instantiate this lower level element, right? So that means we can create a currency factory. So the country can simply ask the currency factory to provide a specific currency based on some information that we provide, right? So here we would provide, let's say, the country type, okay? And then currency factory will provide the specific currency for that country that is required, right? So the functionality to implement currency is now in the factory, whereas the country is only concerned with the details of its own implementation. So basically, to sum up, factory method provides a way to access functionality without caring about implementation. So we introduce a level of separation there, which is always a good idea in software development because that separates functionality and provides a whole lot of advantages. So some of the advantages might be, like I mentioned, separation of concerns, might be testability, right? So it allows us to test elements in separate order. Now, of course, if we have separation of concerns, we also have less impact that some changes might have on other parts that are not intended. So reduction in bug introduction, right? So if you change one part of the code, that means another part of the code will not be affected necessarily, right? So it's always a good idea to separate things, and it allows us it allows testability as well. So let's try it out in our code. Let's implement a small structure here just to show you how you can go about implementing this yourself. So let's go ahead and create a new Kotlin file, and I'm going to call this factory method. Okay, we don't necessarily need a class here. So the first thing we need to do is we need to define the country, right? So I'm going to create a sealed class country. Okay, now there's a few different ways to create the subsequent objects, so the countries, right? So first of all, we could have an object of, let's call it Spain, which is going to be a country. Okay, so it inherits from country. We can also have a class, let's call this Greece, and this implements from country as well. And Greece can also have some information as well, so val some property. Okay, we need the type. Let's put a string here. And then we can also have a data class. That doesn't really matter. Let's say USA, and here also inherits from country. This also requires a constructor, so let's add some property of type string. And we can also have an object inside the class country. Let's say object Canada is going to also inherit from country. All right, so all these objects will need instantiation of a currency. So let's define a class currency. And val currency code is going to be a string. So all these, oh, sorry, this needs to be the constructor here. Okay, so the class currency requires a code for that currency. So all these countries need to have a currency, okay? We don't want the functionality to be provided for each and every one separately, okay? We would like to have some method that provides us the functionality that we require, the instantiation of the currency. So here we can say object currency factory. Okay, and here is the method fun currency for country. And here we provide the country and we give the currency. Okay, and we will simply return. And here we can provide any functionality we want to decide which currency goes for which country. Okay, so for me, I'm going to say when country. Now so when the country is Greece, or let's start with Spain, because that's how we started with. So if it's Spain, then the currency provided is going to be currency of euro. If it's Greece, then the currency is also euro. Now, the cool thing about this is that when we use the when construct, here it must be exhaustive. So it also needs USA and Canada as well, right? So here I'm going to say is USA. Okay, currency for USA is United States dollar. And if it is Canada, okay, then currency is going to be Canadian dollar. So of course this is exhaustive. So if I want to add another country here, let's say class Poland, that extends country, then this when construct will require me to add Poland. So this will not even compile before we add the correct functionality here. So I'm going to comment that out. Okay, so we have, this is the general structure, right? Let's add a test for us to run this code. And I'm going to say class factory method test at test fun. Let's call this currency test. All right, so let's say val Greek currency is going to be currency factory dot currency for country, and here we have to create a Greece object. Does Greece need anything else? Yes, some property. This doesn't really matter, and that's it. Dot code. Okay, so we are taking the code of the currency here. So Greek currency, and then I'm going to print line Greek currency dollar Greek currency. Okay, let's do another one. Val USA currency is going to be currency factory dot currency for country, and here I have USA, and I need some property here as well, dot code. Okay, and I'm going to print line that message as well. USA currency dollar USA currency. All right, so that is the output. Now let's create a few tests, assertions, and make sure you select the assert J ones. Dot assert that here we have Greek currency. I mistyped the Greek here and here. Okay, so Greek currency dot is equal to, and we're expecting the euro here, and I'm going to duplicate that, Command or Control D to duplicate, and USA currency is going to be United States dollar. Okay, so let's go ahead and run the code and see what the output is. All right, there we go. So the print line here is going to give us euros. The second print line is going to give us United States dollar. And of course, the tests will pass, right? We are getting euros and dollars. But the main idea is not the test. It's more the way we construct our factory method. So the factory method is going to know exactly what currency is needed for each particular country that we provide here, right? So that is the main structure of our factory method design pattern. All right, so in this video, we're going to talk about abstract factory. Now, abstract factory, you can think of it as a kind of another level on the factory method pattern that we've studied previously, right? So let's have a quick visual example just to kind of show you an idea of what we mean. Okay, so let's say we have display where we want to display some information, and we have a interface data source. Okay, so this interface can be implemented in multiple ways. Now, what we want to do is the display has to have a separation from the data source. Okay, the display shouldn't really concern itself with where it gets the data. It should really only care about how to actually display the data that it receives. Okay, so it doesn't really care about the data source. Also, what it doesn't care, since it doesn't care about the data source, it doesn't care about how to instantiate that data source or even where to get that data source. Okay, it only really cares about the data. Okay, so that means we have to have a separation of how to instantiate the data source, which is the factory method that we've studied previously, but also how to get the actual instance. Okay, not only how to instantiate it, but where to get it as well. Okay, and this is the abstraction level where the abstract factory comes in. So here we have a data source factory that will provide us with the correct data for our display. So here is the general structure of the abstract factory. It's called abstract factory because we have a abstract factory, surprise, surprise, for our data type. Okay, so we have database factory, network factory, and so on, and these correspond to our data sources. Okay, you can see the let's say interface here that provides the structure for these pieces of data. We have a factory on top of that, and we have a data source factory, a generic type of factory that can then provide information to whatever component needs it in our program. So basically, abstract factory is simply a way to access functionality without caring about implementation and also without caring where we get that object, where we get that data and how we get it. We simply want the functionality. It's one level of abstraction over the factory pattern that we've talked about previously. And some advantages, of course, there are separation of concern just for the factory method, but here again we have a one layer above that, so even more separation because the object that uses the information created doesn't even know where to get it, okay, what type of information it displays. It only cares about the actual information. And of course, testability is facilitated, right? We have an even higher separation of concerns between the two components or multiple components. All right, so enough talk about this. Let's go into our editor and put that in practice, okay? We will learn much better if we actually practice what we talk about. So let's go ahead and create a new file. I'm going to call this abstract factory. Okay, now here I'm going to first create an interface that is my data source. Okay, let's create two types of data source. I'm going to create a class database data source that obviously inherits from data source. Okay, and another class, let's call this network data source of type data source, of course. All right, so we have our data sources. Now let's go ahead and create an abstract factory, abstract class, abstract factory, or rather, let's not call it, let's call it something else, data source factory. Okay, we will put this in, we will put the implementation here in a second, but down below, let's go ahead and create two classes. Network factory, that is a type of data source factory. And we also have our database factory. That is also a data source factory. Okay, so we have our data source factory here. So here in the abstract class, let's go ahead and provide the implementation. So I have, first of all, abstract function, and here we have make data source. So we create the data source, and this returns data source. Okay, so obviously this will be implemented by both of these classes. Okay, and we want a way to retrieve our data source factory, the correct one, right? So here I'm going to create a static method, so companion object, inline function. Okay, I'm going to need the type, so I'm going to say reified t of type data source. Okay, let's give this function a name, and that's going to be something like create factory. Okay, data source factory. Okay, and here we can simply return a when block when t : class, and here we provide all the classes available. So database data factory, network factory, let me have a check. Right, so this is database data source. Okay, so database data source, : class, and here we provide our database factory. Okay, and for the other data source, network data source, : class, we provide the network factory. Okay, and we need to put an else as well. And here we don't really have anything to do, so let's just throw an exception. So throw illegal argument exception. No, illegal argument exception. There we go, the Kotlin one. And here, no parameters. You can put a message if you like. I'm just going to leave it like that. So that is done. Let's go ahead and implement our two classes. Here we need the method make data source. Okay, make data source, and here we have override function make. Sorry, we have that override make data source, and here we can simply return. So what data source do we have for network? We have network data source. Okay, and the same for this one. So option return or alt enter, make data source. We're going to simply return database data source. All right, so that is basically the gist of abstract factory. So now whenever some other data type wants to retrieve some information, we will simply ask the data source factory to give us a factory that we can then call with make data source. Okay, so let's do that in a test. Okay, so I'm going to create a class abstract factory test. And here I'm going to have at test function. Let's call this abstract factory test. Okay, val. So let's create a data source factory. And here we're going to say data source factory. So this is our abstract class. Okay, so we have the static functionality here that we can just retrieve a data source, a factory. So I'm going to say dot create factory. Okay, and now we need to provide a type. So what type do we want? Let's say database data source. Okay, we want the type for the data. And then we have val data source is going to be data source factory dot make data source. Okay, so we have that. Let's go ahead and print line. Here we have created data source $data source. Okay, so just printing out that, and let's do assertions. Make sure you choose the assert j1 dot assert that. We have a data source is instance of, and here we have our database data source class.java. Okay, so we're just making sure that the type returned here is the correct type that we were expecting. Okay, you can of course do this for the other data source that we have for the network. Okay, so let's go ahead and run this. This shouldn't take too long, I think. All right, there we go. So we have created a data source with this ID, and then our test has passed successfully, right? So that is the main idea behind the abstract factory, is that we put another level of abstraction here. So we also provide our factories based on the data type. So we don't necessarily need to know how to create the factories either. We simply provide the data type that we want, and we get the factory that gives us that data type, and then we can use that for whatever we need, right, to get the actual data. All right, so that's all for this video. Thank you for watching, and I'll see you in the next one. Okay guys, so in this video, we're going to talk about the builder pattern. So the builder pattern, you are definitely familiar with it if you worked with Android development before. Basically, a builder is used when we have multiple parameters to initiate. And you are definitely familiar with it because it is used in the Android system quite extensively. Okay, so for example, when we are building an alert dialog, okay, then we have a builder object that we can use to set various properties of that alert dialog. Okay, you don't have to set all the properties, you just set the ones that you are interested in, but you will use that builder in order to create your alert dialog. Okay, so it is used by many developers, obviously by anyone who uses the Android system because they implement it quite extensively, but it is implemented by few developers. Not many people actually use it in their code, even though it's a very, very useful pattern. So what does builder do basically? So it is useful when we have many parameters of a class, okay? When we need to instantiate a class with multiple parameters, some of which are optional, okay? So we don't have to provide all of the parameters. Some of them are optional. Then it is very useful because we don't have to build all the possibilities of constructors, okay? So you might want to let's say you have 5 or 6 parameters, then if some of those are optional, then you would want to build all the constructors possible to allow the users to build your class in different shapes or forms. Okay, so if, for instance, you have 5 parameters, in combination, that will give you about 120 constructors. So obviously that is impractical. Now, Kotlin does solve this problem partially with named parameters. So you could give names to your parameters and pass them like that, right? You don't necessarily need to have all the constructors available. However, the problem with this solution is that it doesn't really work with Java code. And as we know, Kotlin is based on Java, okay? It runs on the JVM. So that means if you are working with any software that is done in Java, then you will not be able to use this functionality with the named parameters. So obviously the builder pattern is very useful here because it allows us to bypass naming parameters and build our class with optional parameters. Okay, so optional parameters. Now, here is a pseudocode of how you would implement the builder pattern. This, if you copy this and put it in your code, this might not work, but we will, after we look at this, we will go to Android Studio and we will implement a functional piece of code there. So here we have, let's say, a component. You can think about this as a dialog or whatever other component you might need that, let's say, has 3 parameters, right? Parameter 1, 2, and 3. Now, the builder is going to be a subclass, right? So we can create a class here that has the same 3 parameters that your component has, but the builder allows us to set them separately, independently, right? So it allows us to have set parameter 1, set parameter 2, and set parameter 3. Now, the important method here is the build. Okay, the build method allows us to give the caller a instance of the component. You can have a look here at the top. The component has a private constructor. Okay, so we cannot instantiate the component by itself. We have to pass through the builder, and the builder through the build method. This is optional. This is obviously optional, but the name is more or less standardized by convention, right? So .build will build you the actual component. So this will give you an instance. Now in the component, when we initiate, okay, when we call this component of this being the builder, then we need to update the values of the parameters in this way, right? So we need to pass the actual values that were given to us by the user. Okay, so let's have a look in Android Studio and create a builder pattern for us. So let's go ahead and right-click New Kotlin file. And here I'm going to call this builder. I'm going to create a class component. Okay, I'm going to make the constructor private. So private constructor builder colon builder. Okay. We haven't created the builder yet, so don't import it. Now, let's define our parameters. So var param1 is going to be a type of string nullable. Var param2 also, or rather, let's put this an int. And var param3 is going to be maybe a Boolean. Okay, and let's create a class builder. All right, so that solves our problem here. Now, this is the builder. This must be initialized, so I'm going to say null. This is going to be null as well. And this one too. Okay, so we have our class builder. Then the builder must have the same parameters. However, I'm going to make them private. So private var param1 is a string and null by default. Private var param2 is an int and null by default. And private var param3 is a Boolean and null by default. Okay, so we have our parameters. Now we need a few functions to be able to set those parameters. So first of all, fun set param1. And here we have param1 of type string. And we're going to apply this dot param1 equals param1. So the reason I use apply here is because every time I use one of these functions, I want to return the actual builder object so that we can apply more functionality to it, right? So then after that, we can chain our calls, set parameter 1, set parameter 2, and so on. Now, fun set param2 of type int, apply this dot param2 equals param2, and then same for param3 boolean apply this dot param3 equals param3. Okay, so these are the setters. Okay, so since these are private, we can only access param1, 2, and 3 through the setters. That is done on purpose. And then we will have fun build. That will simply return us a component of this. Okay, now we will also need getters, but I will show you first why we need getters. So here, outside of the builder class, but inside the component class, we will have an init function, param1 equals builder dot. Now, since we don't have access to param1, then we will need a getter for param1 in order to be able to set it here. Okay, so let's go ahead and create the getter, get param1, and that will simply give us param1. And let's duplicate that, param2 and 3, exactly the same, 2 and 3. So builder that we are passing here in the constructor, builder.get param1. Okay, duplicate that, command or control D to duplicate param2 and param3. Okay, so these are this is the structure of our component. So now let's go ahead and instantiate our component, and obviously I'm going to do that in a test class. So class component test. Here I have at test fun builder test. Okay, and then let's create a component. So val component is going to be component. You will notice that I cannot instantiate it here because the constructor is private, so I'm forced to use a builder. Okay, instantiate the builder. Dot, and here I have the option to set parameters. So set param1 some value dot set param3 true. Okay, the parameters are optional, so I don't have to call param2. However, I do have to call the .build method. Okay, and since I have the build, that will give me the component itself, and now I can do some tests. So assertions, make sure you select the assert j1 dot assert that component dot param1 is equal to what is that? Some value. And then assertions dot assert that component dot param2, param3 is equal to true. And we can also test actually param2 as well. So for param2 is equal to null. Okay, so that is going to be null by default here. Okay, so that's it. Let's go ahead and run the code and try out our pattern. All right, there we go. So we have our builder test has completed. We can also go ahead and print some values. So print line component dot param1, print line component dot param3, and we can print line component. All right, so let's go ahead and run that again. That should give us some printout. So component with its ID, the value, and true. Okay, so you can see how we set the parameters on the builder, and we use the builder to provide various functionality here. All of these parameters are optional. And then we have our component who has all the correct values. So that is all for the builder pattern. So let's talk about lazy initialization. Now, lazy initialization is a very, very useful pattern in general in software development, and even more so in Kotlin, because Kotlin allows us to easily put this in place. So it's a technique for memory management, right? Why should you have a large object in memory if you're not going to use it? Okay, that's the main idea behind it. So for instance, you can think about a network communication system or a database access or things like that, something that might take a lot of memory, a lot of resources that you might not necessarily have. Things like that, you don't really want to instantiate them unless you actually are going to use them. Okay, so basically that's the idea. Initialize a resource when it's needed, not when it's declared. Okay, so you don't want to keep that in memory for a long time unless you absolutely have to. So there's this difference between lazy and eager initialization, right? Eager initialization is you define and instantiate the object as soon as you create the class, whereas lazy, you instantiate it later on in code when you actually use it. If it's small resources, such as small variables or basic types, things like that, strings, arrays, things like that, you don't need to use lazy initialization because they don't take up a lot of resources, right? A string in memory, it's pretty much negligible. So you can simply instantiate your string at the moment where you declare it. You don't have to overuse this technique for lazy initialization. It's only useful for large objects. So here is an example. Let's say we have a class window and we want to display an alert box. Okay, so we have a function show message. What we do here is we instantiate the alert box object, and then when the method show message is called, if it is called, then we display the message and we show it, right? Now here, this is eager initialization, right? We initialize the alert box as soon as we declare it at the top. Now, the difference with lazy initialization is quite obvious. Here we just declare the type, and when we show the message, we check, is it null? And in that case, we instantiate the alert box. Okay, so slight difference, but very important in some cases. Now, Kotlin luckily has built-in lazy initialization, and there are basically two types that you can use in your development. So first of all, you can define your box by lazy, alert box, okay? So that's sort of a declarative way, but it also lets the system instantiate alert box only when it is needed by this keyword, by lazy, okay? So this technique can only be used with val, okay? You cannot use a variable here because this basically ties this box to this instance of the object. So you cannot have a variable data type or a variable value. So this is one way of achieving lazy initialization, but as I said, it only works for val. Now, if you want to use var, then Kotlin also allows that. It provides a way to do that. So the way to do that is with the late init keyword. Late init var, and in this case, you only use var here, box of type alert box. So what this does is tells the system that the actual initialization is not going to be done immediately. It's going to be done at a later point in your code. Okay, so the system is kind of trusting you to instantiate the object rather than requiring it straight away. However, if you use that object without actually instantiating it later on, you will get an error. And here, like I said, it can be used with vars, and it will crash if it's not initialized before use. So you do have to make sure as a developer to initialize your variable before you actually use it. So with that said, let's go to our Android Studio and put that in our code. All right, so let's go ahead and create a new file, lazy initialization. Let me put a capital I here. Okay, so first of all, I want to declare a class alert box that has a var message of type nullable string and null by default. And let's create a function show that simply print lines alert box dollar this instance and dollar message. Okay, so we're just having a class to play around with. So first of all, I'm going to create a class window where we're going to test out our lazy initialization. Val box by lazy. And here we provide the instance of the class, alert box. Okay, and then fun show message. And we provide the message as a string. Okay, and here we have box.message equals message and box.show. Okay, so this will actually allow us to call this function. Okay, and then the box will receive the instance of alert box. Okay, and let's go ahead and create a test class. So class window test. And here I'm going to have add test, fun window test. And let's instantiate the window. So val window equals window, window dot show message, hello window. And let's test for the existence for the non-null of the box. Okay, so I can say assertions, the assert j1 dot assert that window dot box dot is not null. Okay, so I'm just testing that this is not null at the moment where we actually use after we use it. Okay, so go ahead and run this. This should be quite fast. Okay, there we go. So alert box, hello window, and our test has passed. So this has been instantiated at the moment when we actually use it, which is going to be here. Okay, so let's try out our second type of lazy initialization. So class, let's say window2, late init var box of type alert box. Okay, and then we have our function show message, message of type string. Now here we can say box equals alert box. Remember that when we're using late init var, we have to make sure that us as developers, we instantiate the required functionality, right? There's no automatic process like it is here, but here we instantiate it ourselves. If we use it before we instantiate it, we're gonna get a crash, okay? So we have that. Now we can say box.message equals message and box.show. Okay, so in our test, we can say val window2 equals window2. Okay, window2 dot show message second window. Okay, so here we initialize it there, and then assertions. The assertion is similar actually, so I'm just going to copy that and paste it, except it's window2. Before we do that, I want to just print line here, window2 dot box. Okay, just to show you that this will give us a crash. Okay, so let's go ahead and run this, and I want to show you the type of crash that we get. Late init property box has not been initialized. Okay, so this is the error message. If I comment that out and I run this, this will be initialized here, and we should get second window, and our test has passed. Okay, so that is how you would use late initialization. This is quite a useful design pattern. As I said, if you have large objects in memory, if you have smaller ones, you might not want to use this too much because smaller ones are quite negligible in memory, so they don't really matter. It's only for larger objects that this really works. And also be very careful about the late init var, because this can introduce some errors in your code as well. All right, everyone, so let's talk about the prototype design pattern. So the prototype design pattern is a creational design pattern because it basically allows you to copy existing objects. Okay, so let's assume you have an object that in your code that you want to make a copy of in a very efficient way. The prototype lets you do that without relying on their classes. Okay, so you don't need to know the implementation of the class. You don't need to know how the class works. You don't need to have access. For example, an object might have private members that you don't have access to. You don't really need to have access to that in order to implement this functionality. All you need basically is the interface. You are reliant on an interface that tells you what type of object you have. So the main idea here is that the object itself provides the copy functionality, or we could say we have an abstract class that provides us with the correct functionality, with the copy functionality, and that is implemented in all subsequent child classes. Okay, so let's try that out in our code. Let's have a look at how that works. So first of all, I'm going to create a new class. I'm going to call this prototype. Okay, so let's go ahead and create. First of all, we're going to create an abstract class that gives us the functionality to be able to copy or clone these particular types of objects. What I'm going to build here is I'm going to build a caching system that can store shape objects. Okay, so we can store rectangles, squares, circles based on an ID. And then in the client functionality, we're going to have some code that allows us to clone these shapes easily without relying on the implementation of the actual shape. Okay, so the abstract class is going to be the shape, and this implements clonable, the clonable interface here. So we're going to define a var ID of type nullable string that is null by default, and we're going to define also a type of shape that is also a nullable string. Okay, so we're going to have an abstract function draw that allows us to draw the actual shape, and that will be implemented by all the child classes that we will build. And then we have our cloning functionality. Okay, now the cloning functionality is provided by clonable, so we need to override that. Override fun clone. Okay, that will return an any type. Okay, so here we can have var clone of type any null by default. Okay, we're going to try clone equals super.clone, and we're going to catch any exceptions. So if the class cannot be cloned, we're going to catch exceptions of type clone not supported exception. And here we will simply do e.print stack trace. Okay, there we go. And then we're simply going to return our clone. Okay, this needs to be double exclamation mark, because at this point we know that we don't have any errors. If we have any errors, we are throwing them here. Okay, so this is our clone functionality, and this shape abstract class needs to be implemented by all subsequent shapes. Okay, so let's go ahead and declare a class rectangle, which is going to be a shape. Okay, we need to instantiate that. So here we're going to, of course, have an override fun draw method, and I'm going to print line something like inside rectangle, just to print out a message of where this occurred. And here we have : draw method. Okay, so basically we are inside rectangle draw. Okay, because later on we will print this message just to notify the client where that functionality happened, because of course this is a simulation. We cannot really draw a rectangle. I mean, we could, but we don't want to implement those libraries. So here I'm going to initialize the type to a rectangle. Okay, so we want a rectangle type. Okay, so let's add a, let's say a square and a circle. So class square, also a shape. Okay, override fun draw. Here we're going to have a print line inside square colon draw method. And we have an init. The type here is, of course, going to be square. Okay, and that is our square, and we have a circle of type shape. Very similar to the other two, we have override fun draw, print line. We have inside circle colon draw method. Okay, and we have our init type circle. Okay, so basically we have our three shapes, okay, and they are all clonable because they all implement this clone that is part of the abstract class. Okay, so let's go ahead and implement our cache system. Okay, I'm going to make this an object because it's going to be simpler to access its method outside of it. So shape class, shape cache. Here we have a private val shape map is going to be a hash map of string, nullable, and shape. Okay, so we have shapes and we have string IDs. Okay, I'm going to have a fun load cache. So here, let's go ahead and define a few elements. So val circle is going to be a circle. Val, we have square equals square. And we have val, what is the other one? Rectangle. Okay, so we have our elements. So shape map dot put. So let's say we have 1 for circle, we have put 2 for square, and shape map dot put 3 for rectangle. Okay, so we basically now have our cache. The cache just contains instances of these elements, and then we can use that to later on clone those shapes. Okay, so here I'm going to have another function get shape, and I'm going to pass the shape ID of type string, and that will return me a shape. Okay, so val cached shape is going to be shape map dot get of shape ID, and then I'm going to simply return, okay, my cached shape dot clone, that is nullable dot clone as shape dot, what is the, yeah, that should be dot clone. This should be made public so that we can access it outside here. Okay, so basically we have our get shape, we have our load cache, which allows us to initialize our shape cache, and then all that's left for us to do is to actually implement the client functionality. So I'm going to create a class prototype test. I'm going to create a test function. I'm going to have a function test prototype. Okay, so let's see what we should have here. So first of all, I'm going to load cache. I have shape cache dot load cache. Okay, so I'm loading this cache functionality here. And then I will do val cloned shape1 is going to be get or shape cache dot get shape of 1. Okay, so you can see here that I am retrieving the shape without really knowing what that shape is. Okay, I just simply know that it's a shape type, and the get shape will basically clone or make a copy of my prototype, which is the one that I defined here. Okay, so I have cloned shape1, I have val cloned shape2, shaped cache dot get shape of 2, val cloned shape3, shape cache dot get shape 3. Okay, so here I have the clones of these prototypes that I have here. So keep in mind, they're not the same objects, they are different objects, but they are just clones of those objects. Okay, so I'm gonna just call the draw method on each of those. So clone shape2.draw and cloned shape3.draw. Okay, just to get the printouts. And then let's do some assertions. Make sure you use the assert j1 dot assert that cloned shape1 dot type. So for the first one, we are expecting it to be equal to, here that we will have a circle. Then we have assertions dot assert that cloned shape2 dot type is equal to, here we have a square, and assertions dot assert that cloned shape3 dot type is equal to, and this is a rectangle. Okay, so we are expecting that. So let's go ahead and run our code. We should simply get 3 draw methods calls. Okay, and then we are passing those tests. So you can see the prototype method design pattern at work here. We simply have a prototype of circle, a square, and a rectangle inside a cache, and that allows us through the through the clone mechanism, it allows us to get as many clones as we want. Okay, so here I only have one of each, but of course you could have as many as you want. I'm just testing here that the types are what we are expecting for 1, 2, 3, circle, square, and rectangle. So that is the prototype design pattern. All right, everyone, so let's talk about the adapter pattern. Now, if you've worked with Kotlin before, and especially on Android development, you will probably be familiar with the adapter pattern simply because it's used quite often in Android. But let's go through it and see what it is, how we can construct it, and of course, put it in practice as well. So basically, the adapter converts the interface of a class into another interface that the client expects, right? So you can think about it as you have 2 different sets of classes that both have a certain interface. And by interface, we can mean the explicit interface component or part of the class, or it can simply mean the methods that are available, right? If you want to formalize it, you create interfaces. If you don't need to formalize it, or you don't really have that option in the client class, then you don't necessarily need the interface, but it's quite a useful concept to think about it in that way. So basically, it converts an interface into another interface. That is the adapter. It basically adapts your code to the requirements of a third-party library. It can also convert data from one format into another, okay? So if your client library requires data in a certain format, then your data must be converted, must be adapted to the requirements of the third-party class. And the adapter pattern is used extensively in Android. So you have definitely seen this in action in Android, if you've worked with Android, obviously. It is quite a useful pattern. So let me just go into an Android Studio and just show you this as an example, okay? So here I have a project that I actually built in another course, in a separate course. By the way, if you're interested to see how we built this and how we work with this particular adapter, you can find a link to that course in the attached to this video. So basically, this is a country list adapter. What we are doing in this project is we're simply retrieving a bunch of data from a from an endpoint, okay, from an internet endpoint, and displaying it in our application, right? So obviously, the data that comes back from the endpoint is going to be different from the data that we need in order to display it. So that is why we have a country list adapter that basically converts my data, which is the list of countries, into a recycler view adapter. Okay, so you've obviously worked with this before. If you haven't, check out that link here. So obviously this country list adapter will then be used. Let me see where we use it here. We use it as an adapter to convert the data that we receive. Okay, so we update the countries here. We pass the data. The adapter itself converts that data into the right format and displays it. Okay, so this is the adapter pattern applied in Android development. So let's have a look in a very simple way at what the adapter is in this very abstract schema. So let's say we have a third-party library that has a class. We're going to call this adaptee. Okay, this is the class that we're going to adapt to. Okay, so this has, let's say, a specific call. This is the interface, right? We have a function. Obviously, we cannot modify this. This is a third-party library. And even if it was our own library, we don't want to modify it in order to attach it strongly to this other part of our code. We want to keep the parts separated to have separation of concerns, right? So we're gonna keep this class as it is. And here we have our local development, right? We have our local code, we have our target for the client, and this has a certain interface as well. This, we're gonna call this call. Now, how do we make the connection between these two? Obviously, the call cannot simply call this specific call, right? There is a difference in functionality here. So obviously we need an adapter class, okay? In the simplest way possible, the call function will do some processing inside the adapter in order to convert that information so that it can call this interface of the adaptee, okay? That is the basic functionality of the adapter. That is the most simple way you can think about an adapter. So in order to put this in practice and give you a useful information here, we're going to go to our development environment, okay, in the IntelliJ, and let's go ahead and create a class. So I'm going to create a new Kotlin file, and I'm going to call this adapter. Okay, so here we will begin by constructing the third-party library classes. Okay, so I'm going to make this, let's say, third-party functionality, let's say. So this, once we build it, we cannot modify because it's third-party. So here, let's say our third-party functionality can display some data in a certain way, right? So let's create a data class. Let's say display data type. Okay, and this has two parameters, so val index as a float, and let's say val data as a string. Okay, so this is my data that I need in order to display on this third-party library. So next up, we're going to have a class data display. Okay, and this will have a function display data that takes a data of type data display type. I'm going to just call this data, it makes more sense. And let's say we simply display the data. So we're just going to print line data is displayed. And let's do some, let's print out some information. So data dot, let's say index dash data dot data. Okay, so easy enough. We're going to assume that this is displayed to some sort of UI, which will be for us the console. Okay, so this is the third-party functionality up until this point. And then from this point on, we have our code. Okay, so let's say that we have a separate data type in our code. Okay, so I'm going to create a data class. Let's say this data comes from the database. So I'm going to say database data. And this has two parameters. So let's say it has val position as an integer, and then val, let's say amount. Maybe there's some financial information in this database. And this is also an integer. All right, so here we have a class database data generator that simply generates this type of data that we need. So it has a function called generate data that returns us a list of database data. Okay, so let's go ahead and create this functionality. So val list equals array list of database data. Okay, list dot add, let's create an element, database data, let's say 2 and 2. Let's duplicate this twice, and I'm going to say 3 and 7, and here we have 4 and 23. Okay, so we have that, and then we're going to return the list. Okay, so simple enough. We're just generating some random data. We can assume that this will be data that comes from a database. Okay, so we have that. Now, what we want to do is we want to display this data, this list, to our display here, okay, to use the third-party functionality. So how do we do that? Obviously, we cannot simply call this display data with the list that we receive from here. So we have to have an adapter to adapt between our code and the third-party functionality. Now, let's go ahead and create an interface for our adapter. So I'm going to say interface database, let's capitalize this, database data converter. Okay, and this has a function called convert data that takes the data from the database, so data as a list of database data, and returns a list. Let's say we also return a list. We don't have to return anything here, but I just want to return it so that we can do some checking in our tests. Okay, so display data type. Okay, so we're getting this type of data back. Okay, so this will simply be so that we can do some testing, but here we don't actually need to return anything. This will simply convert the data and call the functionality. Okay, so let's go ahead and create our adapter class. Data display adapter of val display. So we get the data display here. Okay, so we're receiving the instance of the display from the third-party library. And here we have the interface database data converter. Okay, obviously we need to implement that functionality. So we have convert data. We need to convert this data into something that we can print out. So here, let's go ahead and create a return list. It's going to be an array list of, here we have display data type. Okay, so that we store the converted data. For Okay, so we have the data here. We need to go through it one by one. So we're going to say for datum, which is singular for data, in data. Okay, and we need to convert this variable datum into our display data type. So val DDT is going to be display data type. Let's create it with the information that we have. So datum dot position. Remember, this needs to be a float, so we're going to say dot to float, and the other one needs to be an integer. Okay, so we're going to say datum dot amount to string. Okay, so we have converted our data. Then we can simply use the display to display our DDT, and we're going to add our DDT to the return list. So return list dot add DDT. Okay, and finally, outside of the loop, we're going to say return list. Okay, so this has converted the data, displayed it, and returned it into a list. Okay, so that is our adapter. So obviously, this works fine, but we need to invoke it. So let's go ahead and create a test class, adapter test. We're going to create a test function, fun adapter test. Okay, so here we need to start creating our data and calling the adapter. So first of all, I'm going to have a generator is going to be database, what did we call it? Database data generator, DDG. Okay, database data generator. Then we're going to have the generated data is going to be generator dot generate data. Obviously, you can combine this, but I want to have a clearer functionality here. Then let's instantiate our adapter, data display adapter. Here we need to pass our data display. So let's go ahead and create data display here. Okay, so we have our adapter. Then we simply need to do val convert data is going to be adapter dot convert data. We need to convert the generated data. Okay, so we have our convert data here. Remember, when we call this, this is actually going to be printed out. Okay, so we should see it. So let's stop here and let's run the code for now and check that the functionality works, that the right data is displayed. Okay, we have 234 and 2723. We should see that printed out in the console. Okay, 234 as floats and 2723 as strings. Okay, so we're just gonna test for that functionality. So let's say assert assertions. Make sure you select the assert j.core one dot assert that let's say converted data dot size is equal to 3. So the size needs to be 3. And you can, of course, go through these values as well to check. I'm just going to go through one of them. So assertions dot assert that convert data of, let's say, the first one, which is actually second, okay, with the index 1. So this is 0, this is 1. Dot index is equal to what should be the first one, 3f. Okay, it's a float, remember. And then we also have convert data 1 of data. It needs to be a string 7. Okay, so we're just checking for the types here as well. Okay, let's go ahead and run this. We should pass our test. Okay, there we go. So we have 2, 3, and 4. These tests pass. So basically, that is the adapter. It allows us to have a third-party library that we cannot change, we cannot touch. We have our own functionality. In our case was data, but we can have basically any type of functionality as well. And here we we adapt our functionality, our data into the required type and use it to call that functionality. Okay, that is basically the adapter design pattern. All right, guys, so in this video, we're going to talk about the bridge design pattern. So to start off, let's look at a hypothetical example. So let's assume that we have a class called ShapeColor. The reason I called it this is to give you an idea of what the characteristics of this class might be. Okay, so this might have a shape and a color. Okay, and from this we can, let's say for example, we can create 4 subclasses, right? So red circle. Okay, so the circle is the shape, red is the color. Then we have blue circle, we have red square and blue square. Okay, so from this you can kind of imagine that we can have many subclasses depending on the characteristics of the main class. And if the characteristics of the main class increase, for example, instead of 2 that we have here, we can have 3 or 4 or more. Okay, you can imagine how many subclasses there might be. Okay, so the number grows exponentially with the number of characteristics in the main class. So obviously this is unsustainable if we want to add characteristics to the type of objects that we have here. So a better solution would be to split these characteristics into different, let's say, inheritance trees and connect them in some way, right? So a better solution might be this. We have a shape that has a circle and a square, and we have a color that is either red or blue. Okay, and here we have the connection between the two. We have this relationship here, contains, right? So this is what we mean by bridge. We split these characteristics into 2 different structures, and we have a connection or a bridge between the 2 here. And if we want to add another characteristic, then we might say something like size, okay? And then we will have a separate tree, inheritance tree, and then we have another connection there. Okay, so that allows us to scale our application and our code. Okay, so basically classes with multiple orthogonal traits, that means traits that are not interconnected between each other, exponentially increases the size of the inheritance tree. Okay, so we saw that. We can imagine 4 or 5, each having 4 or 5 subtypes. Then you can have a tree with a 5 to the power of 5 connections. Okay, so that is quite a lot and obviously unsustainable. So the solution here is to create a bridge and split the structure into multiple classes and interfaces and connect them in some way, right? We have the bridge as an associated reference in the object. So to give you an example of how this works, let's go into our editor and let's go ahead and create a new class here, or a new file rather, and I'm going to call this bridge. Okay, so what we're going to do here is we're going to have 2 structures. So instead of shape and color that we saw in the example, let's have a more practical implementation. We're going to have a device. Okay, you can think about it as a TV or a radio, a device, and a remote control, right, that we can use to perform some functionality on that device. Okay, so here I'm going to create an interface device that has a val, or rather var, volume of type int, and it has a function getName that returns a string. Okay, so that's my interface. I can have as many subtypes of this that I want. So I'm going to create a class radio that is a device. Okay, and here I have to override first the volume, override var volume equals 0 by default, and override my function getName, which simply can return a radio $this. Okay, so the object that is instantiate. And let's have another class. Let's call this device. Let's call this TV as a type of device. And again, override var volume equals 0 and override my getName function. This will return TV $this. Okay, so I have my two classes. Now let's create another structure. Let's call this interface remote. And this has two functions, fun volume up and fun volume down. Okay, easy enough. Now, of course, we can create as many types of remote as we want. I'm just going to create one here. I'm going to say class, let's call this basic remote. Okay, and here is the bridge connection. I'm going to have a val device of type device here and inherits from remote. Okay, so now you can see that we have a connection to the device interface that we've created here. So instead of having a radio remote and a TV remote, we're just going to have a remote with a device connection. So here I'm going to implement my two functions. Okay, volume up is going to say device dot volume plus plus, and let's go ahead and print line a message as well. Let's say $device dot volume, dot getName. Okay, so my device volume up, and let's print the device volume as well. Volume. Okay, so we have that. Now let's do something very similar for the volume down. Okay, so I'm just gonna paste it here. Volume minus minus, so decrement that, and volume down here, and we print out the volume value. Okay, so we have that. Now let's go ahead and create a few objects and play around with these concepts. So I'm gonna say class bridge test. I'm going to create a test method, fun test bridge. Okay, so here let's go ahead and create a TV. Then we're going to have a radio. Okay, then we're going to have a TV remote. And that's going to be a basic remote where we pass our TV. And then I can also have a radio remote. And that's also a basic remote of radio. Okay, so I have my two remotes here. So I can say TV remote dot volume up, and then TV remote dot volume down. Okay, so I call the two functions. Let's actually call this method twice so that we end up with a volume of 1 so that we can test something. Of course, we can test for 0 as well, but that's by default. So let's do the same thing for radio remote dot volume up. I'm going to duplicate this twice, so I'll have 3 of those, and radio remote dot volume down. Okay, so I have my 3 or 4 calls there. Let's go ahead and run this test. We haven't put any tests here, but just to see the output to the console. Okay, this should be quite quick to build and run. Okay, so there we go. We have volume up, it goes to 2, then 1, 1, 2, 3, and then 2. Okay, so that is what I was expecting. And let's put in some tests as well. So assertions, make sure you select the right one, dot assert that TV.volume dot is equal to, what was it, 1 at the end, and then assertions dot assert that radio.volume dot is equal to, and that's going to be 2. Okay, so let's go ahead and run this again. There we go. So we are passing our test. Obviously, we see the output here anyway. Okay, so that is the main idea here. Basically, you have a bridge between your basic remote and your device. Okay, so here obviously you can put as many types of devices that you want. You can have as many types of remotes as you want. The main idea here is that you need to connect the two while you split them so that you can grow this exponentially, right? If you have another class here, let's say a size of the device, then you can perform that connection, that bridge there as well. Okay, so in this video, we're going to talk about the facade pattern. The facade pattern is quite simple and it's quite self-explanatory as well. So the main idea is that we want to provide a simple interface to a complex functionality. Okay, so think about a third-party library that you might be using. You have really no idea what's going on behind the scenes. All you know is what is provided by the interface, okay? And you're not really concerned with how the library does what it does. You're simply concerned with the result that you're gonna get, right? So you can think about a network communication system, okay? Like Retrofit, let's say. You're gonna connect to, using Retrofit, you're gonna connect to a third party or a backend API, okay? And you're gonna retrieve some data. You don't really care that much. Of course, in some situations you might care, but in most cases you won't really care how you get the information as long as it arrives and you have some error handling to manage any problems that might occur, right? So that is the facade. It's basically an interface, or you can think about it more generally as an object or several classes that can provide you some functionality to retrieve or to access some more complex functionality in the background. So it removes the need for complex object and memory management. So you don't know what's going on in the background, you just care about the result that you're gonna get. So in our example about Retrofit, you don't really care about how Retrofit does and what objects it creates in the background, what classes it uses. You don't really care about all of that. You just want the information from the backend API. And of course, it simplifies the client implementation. Since you don't care about all that complex functionality, you can keep it very simple on your end and just interface with the facade that is provided. Okay, so with that said, let's have a look at an example in the IntelliJ IDEA. So let's go ahead and create a new Kotlin file. I'm going to call this complex system store. So the main idea here is that we have a system that can store some information locally, okay, in a very complex way. We're going to kind of assume the complexity, okay? We're not going to actually implement the functionality, but we're going to assume the complexity of this system, okay? So I'm going to create a class complex system store that has a private val file path of type string. Okay, so we're providing the file where we want this information to be stored. We're gonna have a private val cache. That's gonna be a hash map of string and string. Okay, so here we're going to initialize it. We're gonna have an init block. We're gonna print line something like reading data from the file, and here we're going to have the file path, and then we're going to have cache equals hash map. Okay, so we're going to instantiate that hash map, and here we can assume that we are actually performing the functionality to read data from a file. Okay, so I'm going to put a message here, read properties from file, and put to cache. Okay, now we're going to have a function store, and here we're going to have a key of type string and a value of also type string, and I'm gonna have cache of key equals value. Okay, so we're putting this information in our cache. Okay, and here I'm gonna have fun read a key of type string, and that's going to simply return a cache of key. Okay. So cache of key, if that is not null, otherwise empty string. And then fun commit. And that's simply going to be print line storing cached data to file $file path. Okay, so basically we have a cache, and that cache can be committed to the actual file. All right, so we're going to also have a data class user that has a val login of type string. All right, so with that information, we can actually provide the facade now. So we have class user repository. Okay, so this is going to be my facade. Okay, so private val system preferences, and that's going to be a complex system store. Okay, so here we have, we can provide a path, so data/default.prefs. Okay, this doesn't really matter since we're not actually storing the information there. So here we have a function save user of type user. So we want to store the information for this particular user. So we're going to have system preferences dot store, and whatever we want here, user underscore key and user dot login. Okay, so we're just storing that, and we have system preferences dot commit. So we're storing that information to our file. And then finally, we can have another function find first, and that gives us the user, and that's going to be a user of, we need the login. So we're going to have system preferences dot read, and the key is user underscore key. Okay, so basically we have our facade, which has only two functions, which has save and find, or find first. Okay, if we have multiple users in our cache, then we will get the first one. Okay, so let's go ahead and create a test class for this. So facade test. We're gonna have at test fun test facade. So let's create a user repository. So val user repo, user repository. Okay, we're gonna have val user equals user of John, whatever the login name is. Then we have user repo dot save, so we can save our user, and then of course we can retrieve that information as well. So val retrieved user is going to be user repository dot find first. Okay, so this will basically give us the first user that is stored in the cache or in the file. Okay, so there we have it. Now let's go ahead and assert. So assertions dot assert that retrieved user dot login is equal to, and we have John. Okay, so let's go ahead and run this. We should get some printout, and then we should have the test. So basically, we are reading from the file, and we are storing data, cache data to the file. Okay, so basically, we are we are reading from the file. When we initiate the complex system store, we initiate the cache. Okay, and then when we actually save our user, we are storing cache data to the file. Okay, and here we are retrieving our user and making sure that it is equal to what we were expecting, which is going to be John. So basically, that is the facade. You can see that the interface here of two functions, save and find, is much easier than all the functionality that we have here using the cache, using the file on the store, and all the functionality that we have here. Okay, so it's providing a easier way for the user, for the client. Okay, the client is the test function, for the client to access the functionality in the main complex system store here. So that is the facade pattern. All right, so we're going to talk about the decorator or wrapper pattern. Okay, the decorator or wrapper pattern are kind of the same thing. They're just different names for the same design pattern. So the basic idea behind a decorator is that we want to attach some new behavior to an object, okay? But critically, we cannot change existing code, either because the existing code is in a separate library, or we want to preserve some functionality that already exists in our code. But the main idea is that we want to add some functionality to some existing code that we have, some existing object. In addition to that, we can also override some existing behavior, right? So we can change the behavior of an existing object to provide some of our own functionality. So a quick kind of theoretical example, let's assume we have a network communication functionality. Okay, we have a class TCP/IP. If you know a bit about network communication, you would know that this is the protocol that is used to communicate between two endpoints. So this, let's say we have a class that has this functionality to send a packet to an endpoint, right? So this is the kind of lower level functionality that we do not want or cannot change. Then we have a kind of a higher level. We want to add some functionality to it. So we can say we decorate that lower level class with a network communicator that uses the underlying functionality to send a network message. In addition to that, we can keep going. We can add another functionality at a higher level. Let's call this an API service. And then this can add the functionality to retrieve an API that uses all the functionality of lower levels. So that is the main idea. Now let's go to our editor and implement this in a kind of a simpler fashion so that we can understand it better. So let's go ahead and create a new file here. And I'm going to call this decorator. And first of all, let's go ahead and create an interface. And what I'm going to do in this whole program, I'm going to have a coffee machine class that provides some functionality like make a small coffee or a large coffee. And then we will decorate that class with another class that adds some functionality on top of that and overrides some of its own functionality. Okay, so let's go ahead and create the interface coffee machine. Okay, here we have make small coffee, and we have another function make large coffee. Okay, so this is our interface. Let's go ahead and implement it. I'm going to have a class normal coffee machine that implements coffee machine. Okay, and of course we're going to override our two functions, make small coffee, and here we're going to simply print something like normal coffee machine making small coffee. Okay, and here we'll have something very similar. Let me just copy that and I'm gonna paste it here. I'm gonna have also normal coffee machine make large coffee. Okay, so this is my basic functionality. So I want to keep this functionality. Let's say it's in a third-party library. We cannot change it, but we want to add some of our own functionality here. Okay, so I'm going to call this decorator. Now I'm going to have a class enhanced coffee machine that, let's say, it takes a parameter private val coffee machine. Okay, now it extends coffee machine by coffee machine, the parameter that we have. So basically we are using the functionality there so that we don't have to override or implement our own interface, right? We are using the functionality in the object that was passed to us. Okay, so here I want to override some behavior. Overriding behavior. Override fun. We're going to override the large coffee, and I'm going to print line a message saying enhanced coffee machine making large coffee. Okay, so we're going to override this functionality. Overriding behavior. Okay, we also want to add some functionality. Okay, so we're going to extend behavior. So here I'm going to have a function make milk coffee. Okay, so print line, I'm going to say enhanced coffee machine making milk coffee. Okay, here I'm going to use the functionality for my coffee machine dot make small coffee, and then I'm going to add some milk. So I'm going to say print line enhanced coffee machine adding milk. Okay, so I've extended the behavior. I've decorated the existing coffee machine, the normal coffee machine, with my extended functionality. Okay, so let's go ahead and call this functionality. So I'm going to have a class decorator test. I'm going to create a test function, fun test decorator. Okay, so let's go ahead and create some objects, normal machine, normal coffee machine, and then I'm going to have a enhanced machine, enhanced coffee machine, and here of course I need to pass the normal object, normal machine here. Okay, so let's go ahead and say enhanced machine dot make small coffee, make large coffee. We have the small coffee as well, as of course, because we have the functionality of the decorated object. Okay, so we can call that. We can call enhanced coffee machine dot make large coffee, and then we have enhanced coffee machine dot make milk coffee. Okay, so I think that should be it. Let me add some print lines here so that we can differentiate between the printouts. Okay, there we go. So let's go ahead and run the functionality. There we go. So the first one, enhanced machine makes more coffee, it simply uses the functionality for the normal coffee machine. Then when we make large coffee, we are using the enhanced coffee machine here because we have overridden the functionality, right? So of course we will use this one. And then finally, when we're making milk coffee, what happens? We are print lining this. So we get this printout. Then we are using the functionality of the regular coffee machine. So we get normal coffee machine here. And then of course we are adding the milk. So enhanced is called as well. So you can see how we decorate this functionality for the normal functionality for our coffee machine. So that is the main idea behind a decorator pattern. We are kind of encapsulating or wrapping or decorating our existing functionality with a new class, new functionality that we want to have in our code. Okay, so in this video, we're going to talk about the composite design pattern. So let's start off with a quick hypothetical example here. So let's say we have a computer. Our computer is made up of different components that they themselves can be made up of various components, right? So here we have a computer that's made of a hard disk, a processor, and a memory. And the memory itself is composed of read-only memory and random access memory. Okay, so different types. So you can see that we kind of have this tree structure. Okay, the computer has some subcomponents, and each subcomponent has its own subcomponents. Okay, we can build this kind of tree. So let's say we want to find out the price of the computer. How do we do that? Well, basically, we need to calculate the price of each of individual component, add those up, and that is our final total price. Okay, now in a real world situation, in a complex program, you might have a few issues with this approach, right? You couldn't, maybe you need to ask each individual component what the price is, or what the value that you're interested in is, or what the functionality that you want computed how that can be achieved, right? So in a real world situation, what we would like is to have this kind of tree structure where each individual component provides its own functionality, and we are able to compose all that functionality into a tree structure that we can then manipulate individually, right? So that is the main idea behind a composite pattern, is the way we structure our code and our functionality. So basically, we are composing our object into tree structure to achieve some functionality, right? Either to get some information from each subcomponent, or provide some piece of code, some functionality, and so on and so on. So this design pattern works when the core functionality can be represented as a tree. Now, of course, you don't need to apply this to the whole application. Okay, you can apply it to parts of the code that work well with this structure, with this tree kind of pattern, right? So the main idea is that we can manipulate many objects as a single one. Okay, so in our example, we can manipulate all these components as a single computer. Okay, we are structuring this in a way that the computer contains is a composite of all its subcomponents. Okay, so let's try this out in code. Let's go ahead and create a new file, and I'm going to call this composite. So we're going to create a computer structure, and we're going to add these subcomponents that will allow us to calculate a price for our computer. Okay, so first of all, I'm going to have an open class. Let's call this equipment as a general notion. Okay, I'm going to have an open val price as an integer, and I'm going to have a name as well as a string. Okay, so this, I think we're missing a comma here. And of course, this is part of the constructor. It's not part of the body of the class. Okay, so this needs to be, these are the variables that go into the constructor of equipment. Okay, so let's create an open class composite. Okay, we have a name of type string, and this extends equipment, and the price by default is 0, and we pass the name here. Okay, so basically this is the composite of all the subcomponents, sub-equipments that we will have. So first of all, this will have a private val equipments, and this is going to be an array list of equipment. Okay, now override val price as an integer, and we're gonna override the getter. We're gonna have equipments dot map it dot price dot sum. Okay, so we're just gonna calculate the sum of all the equipments that we have in our array list. And then we're gonna have a function add equipment, which, as you might expect, will simply do equipments dot add equipment. Okay, so we have the functionality to add a component to our composite. All right, so that is basically the structure that we need. Let's go ahead and define some of the concepts, the components that we have in our code. So we're going to have a class computer, and that is going to be a composite. Okay, the name is going to be, let's call this PC. Then we're going to have a class processor. That will be an equipment. The price is, let's say, 1000, and that's going to be a processor. We're going to have a class hard drive, also an equipment, 250, and this is going to be a hard drive. Of course, this needs to be a string. Then we have our class ROM, or rather, let's create the memory first. Memory as a composite of memory. Okay. Then we have the class ROM read-only memory, right? This is going to be an equipment. And let's do 100 and read-only memory. And class RAM is going to be an equipment, price 50, or let's say 75, random access memory. Okay, so we have our objects. Let's go ahead and create the functionality to compose them. Okay, so we're going to have class composite test. We're going to have a test here, and we're going to have fun test composite. So first of all, we're going to say memory is going to be a object of type memory dot add ROM dot add RAM. Okay, so we're going to add both of these components to our memory. Next up, we're going to have val PC is going to be a computer. Okay, dot add. So we're going to add our memory. We're going to add a processor. Okay, create an object there, and we're going to add a hard drive. Okay, so we have our complete structure, and we're going to print line the price for our PC. PC price $PC dot price. Okay, so that's it. So let's assert. So assertions from assert j dot assert that PC dot name is equal to, what name did we give it? PC. And assertions dot assert that PC dot price is equal to, so what's the price? 1,250, 350, 425, 1,425. Okay, so let's go ahead and run our code. There we go. So we have our PC price 1,425. So you can see that we've built this kind of tree structure here where we can have composites made of subcomposites, made of equipment, and so on and so on. Okay, so the price is going to be easy to calculate since we have this kind of tree structure in our code. And for us, it's quite a simple functionality because we are simply interested in the sum of a certain value. But of course, you can provide some functionality there for each of the subcomposites to call whenever you want to perform some type of functionality, right? That is simple. That is done simply by calling each individual element of our tree. And we have, like we said, the composite allows us to treat a larger number of components through a single object, which in our case is the PC. Okay, so we can say PC.price to calculate the price of all the subcomponents of that element. So that is the composite pattern. Okay, so in this video, we're going to talk about the proxy design pattern. So first of all, let's have a look at a kind of an example of where this design pattern might be useful. So let's say you have a disk that stores some information, some files, or you could have a database or whatever that is. It stores some data. And you have various clients that access this particular disk, okay? Each individual client can ask for the same file on the disk, or they can ask for various files. Now, of course, this is not very efficient because if one of the clients asks for a certain file, the disk takes a long time to retrieve that information and provide it to the client when it's not actually useful, right? If one client accessed a certain file, then the second client should be able to retrieve that same information a bit faster. So that's where, let's say, caching might come in, and the proxy design pattern. So here we have a disk proxy that provides some caching functionality, but it also allows our clients to retrieve the disk information in the same way as if they were interrogating the disk directly. Okay, so that is the proxy design pattern. It's basically a way to provide some functionality before and or after calling an object. Okay, it's a proxy for an object. It allows us to call a object in the same way, but provides some extra functionality. Now, you might notice that this proxy functionality, this proxy design pattern, is quite similar to other design patterns that we've studied previously, okay? But there are quite subtle but important differences. So first of all, it's very similar to a facade, okay? So you might remember that facade is a way to provide some interface to access a complex functionality in the backend. The difference here is that proxy will have the same interface for the functionality behind it. It's just that it adds some extra code or some extra things to do before or after accessing the required functionality. Okay, so it's similar to facade, but it's not exactly the same thing. It's also very similar to a decorator. The difference here is that proxy kind of manages the lifecycle of its object, whereas in a decorator pattern, it is the client that manages the lifecycle of the object, right? So the client tells it when to create the object, when to destroy it, when to do certain functionality, whereas the proxy is kind of it's a stand-in for the exact same object, except that it adds some extra functionality before and after, okay? Exactly like our example here, we simply provide caching, but from a client's point of view, it is accessing the exact same object, the same disk, okay? It doesn't really care what is happening in the proxy while it's accessing it. So let's try this in code. Let's go ahead and create a file. Okay, I'm gonna call this proxy. So here, let's say we have an interface called file, or rather image. Okay, so let's say we have the image interface that simply has a function display. Okay, and we have a disk that we want to retrieve this image from. Okay, now we have a class real image, okay, that will be retrieved from the disk, and here we have a private val file name of type string, and this implements the image interface. Okay, so we're gonna have here override display, and here we simply print line some message, real image displaying $file name. Okay, so we want to see how we can display that image. Next up, we have a private fun load from disk. And here we have our file name of type string. And we will print line a message, real image, loading $file name. Okay, and we're going to initialize this object by loading from disk. So I'm going to call load from disk file name. Okay, so this is our real image. Now we also have a proxy image, which also has a private val file name of type string and inherits from image. So here we have our private val real image. Let's make this a var and make it nullable. So real image equals null. Okay, and then we have our display that will simply have a print line. Now here we have proxy image displaying $file name. So here we are implementing a very rudimentary cache. Okay, so here we can say if real image is null, then real image is going to be instantiated with the object real image with the file name. Okay, so then if this is not null, then we don't do this functionality and we use the image from cache. Okay, so real image dot display. Okay, at this point we can be sure that we have something, so double exclamation mark there. Okay, so either we have nothing in our so-called cache and we instantiate it, or we have something and we simply display what we have. Now here we have our class proxy test, and we have our function test proxy. Okay, and here let's go ahead and instantiate some objects. So val image is going to be a proxy image, and let's give it a test.jpg. Okay, so we're going to call, so first of all, load image from disk in the first instance because we don't have anything in our proxy. So we're going to say image dot display. Okay, let me print line a separator here. And then finally, we're going to say load image from, let's call this cache, although it's not really cache, it's just a variable that stores some value. But we can assume that that's a cache, and we're going to call image.display. And let's run the code and see what we get. All right, so running the code, we can see that the first time that we run, we get this displaying test.jpg from the proxy image. Okay, we are expecting that. It's the first line. But then we see loading. Okay, so this only occurs when we are loading the image from disk. And then after that, we are just displaying the image. But the second time we call that, of course, this is a cache, so we do not load the image anymore. We are just displaying it, the image that we have in memory. So you can see that with the proxy, we have implemented a very rudimentary cache system that provides us with some functionality before we actually display the image. Okay, so the functionality is just print a message and instantiate or use the cache. Of course, you could add more functionality here. You can do a lot more things depending on what your software or your project requires, but this is the general structure. It's simply providing an object with the same interface for our existing object. So that is the proxy. All right, so in this video, we're going to get started with the first behavioral design pattern, which is the observer. The observer is quite a common design pattern simply because it's quite useful. It allows us basically to notify a set of subscribers of a certain event that might happen. Okay, so basically, at its core, it defines a subscription mechanism. So you can think about it in real life. When you subscribe to a magazine or to some service, every time something is published to that service, you get a notification because you are subscribed to it. So that is the same idea here. The observer pattern allows a component to be an observer of a service. And the service, as soon as it is updated, will provide a notification to its observers or subscribers. So it allows us to notify multiple objects simultaneously. So you can have as many observers as you want inside your that are going to be notified. And then once something happens, all of these observers will be notified. And basically at its core, it defines a one-to-many relationship. So let's have a look at a schema to see how we can implement this. So basically here we have an event manager that has a list of subscribers, or we could call them observers, right? It's the same thing. So a list of subscribers, which are objects that are interested in notifications coming from this event manager. Now keep in mind, the event manager can provide various types of notifications. So it doesn't have to be limited to a certain type of notification. If it does make sense to notify of multiple types of events, then that can be implemented. And it has a function to notify subscribers. Now here on the left side, we have an event generator. As soon as an event is generated here, the event manager will notify all its subscribers. The event manager defines an interface, okay, that can be used by other objects in the project to be able to attach to these notifications. And here we have a number of subscribers that all implement this subscriber interface and have a function that will be called whenever there is a new event that has occurred. So this is the general schema. It's not very complicated. It might look a bit complex in code, but it's quite simple at its core. So let's go into our code and implement this structure. So I'm going to create a new Kotlin file called observer, okay, for the observer pattern. Now, what we're going to do here is we're going to have a file that can be opened and saved, okay? And those are the two events that we will have in our system, open file and save file. And whenever one of these events will be called, we will notify a couple of observers, okay? One of the observers is a logger, and another one is an email service, an email notification service, okay? So both of these logger and email service are interested in the file operations. Okay, so we will implement this structure. So first of all, let's define an interface for our subscribers. Okay, I'm going to call this event listener. And this event listener has a function update where you pass the event type. Okay, here we have two types of events, open file and save file. Event type of type string, that is nullable, and the file that has been accessed. So I'm going to call this file from Java.io. Okay, so this is my event listener interface. Now I'm going to create a event manager. Okay, and here we can get multiple operations. So var arg operations of type string. Okay, the first thing that it needs is a list of listeners. So var listeners is going to be an empty hash map that has a string and array list of event listener. Okay, so it has a hash map of string and event listeners. Okay, so let's initialize this. For operation in operations, listeners of operation is going to be an array list of event listener. All right, so we've initialized our listeners list. Then we have function subscribe. So this will allow our listeners to subscribe to events. Okay, so this will obviously take an event type of type nullable string and a listener of type event listener. Okay, so here we simply say val users equals listeners dot get of event type, and then users dot it's nullable, so question mark dot add listener. Okay, so of course we have multiple types of operations, multiple types of events. Therefore, we must have a list or an array list for each one. And here we have our types. We get those, we get the array list, and then we add our listener to it. Okay, so that is our subscribe. Now we have an unsubscribe function. Here again we get the event type and the listener, and we do kind of the reverse operation. So again, val users is listeners dot get event type, and then users question mark dot remove the listener. Okay, so we have our subscribe and unsubscribe. Now, of course, since this is an event manager, we also need the notify method. Okay, so notify. So we're notifying an event type, and we are notifying an operation because we need the file here as well. We need to pass it here. So file of type file. So let's get the users that are interested in this event type. So val users is going to be listeners dot get event type. And for all of these users, if they are not null, so users question mark dot let, for listener in user, so it, then we will say listener dot update. So the update method has event type and file. Okay, so we are notifying all the users interested in this particular event type. Okay, so we have our manager. Now we need an event generator. Okay, so we're gonna have a class, let's call this editor. Okay, because we are using files, so the editor will generate our events. So var events of type event manager. Okay, we need a reference to this. And we will have an init block where we say events equals event manager of. So what kind of events can we have? We can have open and we can have save. Actually, we can even combine these calls, these instantiations. Okay, so we have our events. Then we have private var file is of type file, nullable equals null by default. Okay, so we have a few methods in this editor. So first of all, fun open file, and we have file path of type string. So file is going to be file of file path. Okay, and then events dot notify. So we want to notify all our listeners on our event manager. So notify of an open event and on the file. Okay, so this is our open file operation, and we have also save file. Okay, if file is not null, then events dot notify save and file. And we can actually refactor this one a bit. File question mark dot let. There we go. So if the file is not null, then we notify of the file save. So that is basically it for our editor. We have two operations, open and save. We have our manager with the event types open and save. Okay. Remember, we can add here as many operations as we want. And that is pretty much it. All the subscribers will be notified. Okay, so that is all. Now we need a couple of listeners, right? So keep in mind that we have our event listener, but we don't have an instantiation of that interface. So let's go ahead and do that. Class, let's say email notification listener. Okay, so this basically will simulate sending an email if we receive a certain event type. Okay, so here we have private val email of type string, and this implements the event listener interface. Okay. So we have a function to implement, update, and that will simply be a print line. We're going to print a message to the console saying something like email to email. Someone has performed $event type. Okay, keep in mind that we will receive the event type here. Someone has performed event type operation with the file $file.name. And I think this needs a question mark as well because it can be nullable. So that is all for the email notification listener. Now let's create another one. Let's say log open listener. Okay, and here we will simply get a file name of type string. And of course, implements event listener. Of course, we have to implement our method update, and here we will simply print line. Okay, we will simulate some functionality here. Save to log $file name. This needs to be a var, I think. Okay, so save to file name. Someone has performed $event type operation with the file $file $name. File.name and add the question mark. Okay, so we have our listeners. So let's go ahead and implement some functionality. So class observer test. I'm not sure we will add assertions, but at least we will have we will be able to run our functionality. So at test fun test observer. Okay, so the first thing we need to do, we need an editor. So val editor equals editor. Next up, we need events. So we need to subscribe to certain events. So editor.events. Okay, keep in mind events is our manager. Okay, so editor.events.subscribe. Here we have two types of events. Okay, we have open and save. So for example, for the open event, we will have the log, let's say. So we will pass log open listener. And here we need a path. So path to log file.text. Okay, so that is our open event. And let's add another one, event editor.events.subscribe. And here we have our save. And then email notification listener. And here we need just an email, test@test.com. Okay, so let's go ahead and call this. So we're going to say editor.openFile test.text, and we're going to say editor.savefile. So for the open file, we should get a notification for the log listener because it's subscribed for open events, and for save file, we will get a notification for the email. Okay, so let's go ahead and run this. All right, that should not be too fast. I just missed something, I guess. Let's see. Yes, of course, I need the actual function here. Run that again. Okay, so there we go. So basically, when we open the file, the log listener was notified here, and we get this operation, right? Someone has performed open operation with the file test.text, save to log, and then when we do save file, we get the save, the email notification listener, we get email too. And of course, we can subscribe email notification listener as well. So let me define the log listener here. Okay, I'm going to move this here. I'm going to call this val and log listener. Okay, and let me define a val email listener here. Is going to be email notification listener email. Okay, but I can subscribe my email listener to open events as well. So editor.events.subscribe open and email listener. Okay, so now my email listener will get both open and save notifications. Okay, so let's go ahead and run. Okay, so first of all, we subscribe the log listener, so that's going to be the first one notified. And then email, someone has performed open operation, someone has performed save operation. So you can see that now the email listener is subscribed to both types of events. And of course, we can define as many listeners as we want, and we can define other listeners as well. As long as they implement the event listener interface, then they will be notified and they can do whatever they want with that notification. So basically that is the structure. As you've seen, it's not very complex. We simply need a event generator, an event manager that handles some listeners, and then our listeners simply subscribe to events and get notified. So that is the observer pattern. All right, so in this video, we're going to talk about the chain of responsibility design pattern. So what does that mean? Basically, it implies that there is a chain of so-called handlers. A handler is obviously a class or an object that can handle a request in some way. Okay, and we define a chain of handlers to process a certain request. This has some obvious advantages. So when you have multiple operations that need to be performed on a request, you can have a chain where each object in that chain handles its own operation, right? Rather than putting everything in a single class, you can have separate classes for separate operations. Okay, so that obviously helps with separation of concerns. So that is the main idea, defining a chain to process the request. Now, each handler, if we are talking about a chain, each handler needs to have a reference to the next handler, so that when a request has been processed in a certain way, or even if the request cannot be processed, then we can send, or the handler can send the request on down the chain to the next handler to perform its operations. And each handler then decides to process the request, decides whether or not to process the request. It has the option to not process it and simply pass it on to the next handler, and or pass it on, right? So there are two schools of thought here. One that says each element, each handler handles the request cannot pass it on. Okay, so the request has been handled. Or we can have a system where each handler adds its own functionality and then moves the request onwards down the chain. So these are two different strategies that obviously depend on the requirements of the project, right? We will see an example of this. And requests can be of different types, okay? So we don't necessarily have to have a single type of request. We can have multiple types, and we can actually send the request to various handlers in the chain. So we don't necessarily have to send the request to the first handler in the chain. We can send it in the middle somewhere if the functionality requires us to do so. So a quick visual representation of this: we have a request that is passed to a handler. The handler has the option to process the request, so then we get a result. Or if it cannot process it, it moves it on to the next handler to see if that one can handle it. Okay, so this is the situation where the handler, once the request is handled, then the handler breaks the chain. Okay, so we don't send the request onwards. So the request can move from handler to handler. At one point, it will be processed. If it cannot, then the request fails, or depending on the functionality of the project, you can have another way to handle that request. So that is one way. It's basically a chain, but actually there is another way to kind of structure this design pattern. So this is the chain, but we can also have a tree structure. So this is very evident in the way Android handles operations on its UI, okay, in its XML layouts. So here, for example, let's say we have a click of a button. That button will either handle that request, okay, or pass it on to the relative layout. If the relative layout cannot handle the request, it will pass it on upwards to the constraint layout, which of course can either handle it or let the request simply die out. Okay, so this is the chain of responsibility represented in an Android setting. If you've worked with Android before, you would be familiar with this structure. That is the typical chain of responsibility design pattern. All right, so let's move on to the IDE and put in practice, put into code one of these design patterns. Okay, so I'm going to call this chain of responsibility. Okay, so first of all, let's go ahead and define an interface called handler chain. Okay, and so what we're going to do here in this program is we're going to simulate a system that adds headers to a HTTP request. Okay, so the HTTP request has authentication headers, it has caching headers, it has a whole lot of headers that we can add to that request before we send it on to the backend API. So here we're going to simulate adding a few of these headers to a request. So the interface handler chain has a function called add header. And here we're going to have an input header of type string, and the whole function returns a string. So basically, each handler that implements this interface receives a input header and returns a updated header. Okay, so we are here in the situation where each handler both handles the request and passes it on to the next handler in the chain. So let's go ahead and implement the interface. First of all, I'm going to have an authentication header that has a val next, has a token. Okay, so the authentication token of type string question mark, and it has a next, which is a handler chain that can be null. And here we implement the handler chain interface. Okay, so we're going to have an override function add header. Okay, and here we will simply return directly $input header. We're going to put a new line without any spaces. We're going to have authorization colon space $token. So these spaces here are quite important, or lack thereof, are quite important because when we will test this functionality, we need to know whether there's a space or not. Okay, so we have our token, and then we need to pass it on. So .let next question mark .add header it. And if we don't have a header, we're going to say question mark colon it. Okay, so we're just going to return the result. Okay, so this is our authentication header. Now let's add another header. Let's say content type header. Here we're going to have a val content type of type string and val next of type handler chain that can be null, and it implements the interface handler chain. So again, override add header. We're going to simply return $input header /n, and here we add this particular header. So we're going to have content type space dollar. We have the content type there, .let, and the .let is exactly the same. Okay, so we just copy and paste that. Okay, and let's add a final one, the body payload header, val body of type string, and val next handler chain equals null by default. And this will be a handler chain as well. Override the function simply return input header /n, and here we have body. Okay, and of course .let next add header. Okay, so this is my chain. Now these are just the headers. The chain has not been constructed yet, so we will do that next. Let's go ahead and create our test class. So class chain of responsibility test. We're going to add a test function, fun test chain of responsibility. All right, so let's go ahead and create our elements. So first of all, val authentication header is going to be an authentication header. Authentication header, and here we need to pass our token, right? So here we have our token 1, 2, 3, 4, 5, 6, whatever that is. The next one is null by default, so let's just leave it at that for now. Then we have content type header. Is going to be a content type header. So the content is going to be JSON. And then we're going to have a message body, or what did we call it? Body payload header. It's going to be a body payload header. And here we need to have a body in the form of JSON. So we're going to have body : and curly braces. We escape the quotes, username, escape the quote, space equals space, escape the quote again. You can put your username here. I'm going to put John, and escape the quote again. So body is going to be username John in JSON format. Then let's construct our chain. So authentication header.next is going to be the content type header. And then I think this is a val, and we need to change it to a var so that we can update it. There we go. Okay, so authentication header.next, and then content type header.next is going to be the body payload header. Okay, so we have our chain. So let's go ahead and create a message. So I'm going to say val message with authentication is going to be authentication header dot add header, and the message is going to be headers with authentication. Okay, and then let's just go ahead and print line the message with authentication. So here we simply call the first header in our chain. Okay, but of course we can call a secondary header as well. So I'm going to say val message without authentication. And here, instead of calling authentication header, I'm just going to jump into content header, add header, and here we'll have headers without authentication. Okay, and I'm going to print line this message as well, message without authentication. Okay, so let's go ahead and run this just to see the output that we get. All right, so here we have our, we should actually, you know what, let's put a divider here so that we see where those two start and finish. Okay, so the first one, you can see headers with authentication. We have our authorization, content type, and body. And then without authentication, we have everything else apart from authorization. So let's add some assertions as well here. So assertions, use the assert j1 dot assert that message, I'm not sure, there we go, message with authentication dot is equal to. Now here I'm gonna have this type of string. So I'm gonna have headers with authentication, then I'm gonna have authorization 1, 2, 3, 4, 5, 6. I'm gonna have content type JSON, and I'm gonna have body curly braces quotes username space equals space John. Okay, so I have that. So I'm gonna copy this and paste it. And this time we're gonna have message without authentication, and I'm just gonna remove the authentication here. Let's go ahead and run. And there is a difference apparently. Let's click to see what the difference is with or without. Okay, so I forgot to change this. Okay, now run that again. There we go. So we have our tests that are set in place so that our functionality doesn't change without breaking the test. So that is basically the idea. You set up a certain chain of handlers, or you could set up a tree of handlers as well. It really depends on how you want to structure your functionality here. And then your request passes from handler to handler without the client worrying about who should come next. Okay, the chain knows that once it is built, and then the functionality just processes the request and returns the correct result here. So that is the chain of responsibility design pattern. So in this video, we're going to talk about the command design pattern. Now, the command design pattern is quite simple to understand. It's basically a request that is wrapped in an object that contains all its relevant information, right? So that means each request can be handled separately, sent to the required place where it needs to be processed. It can be queued. It can be handled in whatever way the program needs it, right? It's just basically a object that handles a certain request and contains all the required information for processing that request. That is the gist of the command design pattern. So the command object is then passed to the correct handler. You could have an instance of let's call this a dispatcher that can send the right command to the right place, or it can be sent directly to the processor where it needs to be handled, right? So you can think about it as, let's say, an editor software that has a certain specific command, like copy a text or paste or cut or whatever that is. You can contain all of that information that is required to process that command and do the operation inside a single object, and then you can pass that object around in code. Okay, so that is the basic idea. Let's go ahead and implement a simple structure to illustrate that design pattern. So I'm going to call this command. Now, first of all, I'm going to define an interface command that has a function execute. Okay, so basically the command object that implements this command has a execute method that allows us to do the processing. And here I'm going to design a simple online ordering system that allows us to have two commands. First of all, to add an order, okay, with a certain ID, and then to pay for that order. Okay, so we're going to have two types of commands. So first of all, let's go ahead and define a order add command. Okay, I'm going to have here a val ID of type long. And then this implements the command interface. Okay, and of course I need to override the execute method, which simply says println adding order with ID $ID. Okay, so that is my order add command. Now I'm gonna create a class order pay command, val ID of type long. That is also a command. And I'm gonna have the execute method, and here I'm gonna println the paying for order with ID $ID. Okay, so we have our two types of commands. Now I'm going to create a class command processor. Okay, and this class will basically store a queue for commands, and then it will process those commands as well. So I'm going to have a private val queue that is going to be an array list of, and here I have my command. So it's an array list of commands. Then I have a function add to queue, and here we have a parameter command of type command, obviously. Okay, and this one will return us a command processor. Okay, so the reason I do that is so that we can chain these operations nicely. Okay, and I'm gonna have simply apply queue dot add my command. Okay, so that is my add to queue, and I have another function called process commands. Okay, also returns a command processor, and that will be apply. Here I have queue dot for each. I will do it dot execute. So I will execute all the commands in the queue, and then I will simply say queue dot clear. Okay, so that is the process commands function. Okay, so I have pretty much everything I need. All I need is to create a couple of commands, add them to the queue, and then process all of them. So I'm gonna have fun, or rather class command test. I'm gonna create a test method, fun test command. So command processor, okay, instantiate that. Then I'm gonna add to queue. Let's create a command, let's say order add command. And here you can give it whatever ID you like. Let's just add 1L dot add to queue. Let's do another order add command. The ID is 2L. And then dot add to queue order pay command. I'm going to pay for the command 2L. And then dot add to queue again, order pay command. Order pay command. And here I have 1L. Okay, and I have all of these, and then I can do process commands. Okay, so that will simply print out the messages for the execute of those messages, of those commands. So let's go ahead and run the code. And then we get adding order 1, order 2, paying for order 2, and then paying for order 1. Okay, so you can see basically that we have this command object that we can use in our code. So in this instance, I'm just passing it to a command processor, but you can of course store more information there and pass it along in your code to do some operations on it and then execute it at one point. Okay, all commands have this execute method in this particular case. So there you go. That is the command design pattern. All right, so in this video, we're going to talk about the strategy design pattern. So this one is quite interesting. It basically describes a class where behavior or algorithm can be changed at runtime. Okay, so we can define a class that is sort of a container for a certain algorithm, and then we encapsulate that algorithm in a separate object that allows our class to call that specific algorithm. Okay, so we create objects that create some logic, okay, that we want to have in that particular class. And then the context object can handle pretty much any algorithm object as long as it implements a certain interface. And these algorithm logic objects can be changed at runtime depending on what the requirements are. So we give the client the possibility to change the logic that is applied by a third-party class. Okay, so this is very useful when we want to be able to add some functionality without changing the program structure and without changing other objects and classes that we already have. We can add and remove algorithm objects at runtime depending on the requirements of the client that is calling the functionality. So to give you a quick schema, here we have a client. Here we have a class that can change its algorithm depending on which one is provided by the client. And then we have various strategies here that can be substituted in the executor class. Okay, so this is the general structure. Let's have a look in the editor and put this into a quick example. So I'm going to create a new file. I'm going to call this strategy. Okay, so here, let's go ahead and create a class printer. Okay, so the printer class allows us to print some message, okay? And we will have various algorithms that we can pass to this class to change the way we print the information. So here we will have a private val string formatter strategy. That is going to be a lambda expression which takes a string and returns a string. Okay, so we can apply some functionality that we will provide later on at runtime. We will apply some functionality to this string formatter strategy. Okay, so here we have a function print string, and we have string of type string, and here we will print line the string formatter strategy of the string that we receive. Okay, so let's call this message, might be a better name for it. Okay, so basically we apply the algorithm here to our message, we get a string back and we print that message. Okay, so let's define a couple of lambdas that will symbolize our strategies. Okay, so val, let's say this is lowercase formatter. Okay, so that's going to be, that's going to take an it of type string, and that's going to do it dot to lowercase. Okay, so it will simply put everything to lowercase here. Okay, so for lowercase formatter, and then we have uppercase formatter, and it's going to be exactly the same thing, it of type string, that will give us it dot to uppercase. All right, so we have that, we have our printer, we have our strategies. Let's go ahead and call this. So I'm going to say class strategy test at test function test strategy. Okay, so here let's go ahead and create an input string. So input string is going to be lorem ipsum $sit amet. So basically I want to have uppercase and lowercase as well. Okay, so we can see the difference when we print it out. All right, so I'm gonna have a val lowercase printer is going to be a printer of lowercase formatter. Obviously, this is passed in the constructor, so here I'm instantiating the object printer with a lowercase formatter, but obviously I could pass this in the method as well. Okay, so that will allow me to pass this print string here as well. You have multiple options. Okay, so here I'm gonna say lowercase printer dot print string my input string. Okay, and then I have val uppercase printer is going to be a printer of uppercase formatter and uppercase printer dot print string input string. All right, so that's all there is to it. Let's go ahead and run our test string. And then we get, as we were expecting, everything in lowercase and everything in uppercase. Okay, so all of these should be fine. So there we go. We have our class that can receive a strategy at runtime. So basically, the client will decide what kind of strategy will the printer follow. And then we pass either a lowercase formatter, uppercase formatter, or you can define your own formatter here, your own strategy that you can pass to your printer. Okay, so that is the strategy design pattern. All right, so let's talk about the state design pattern. So the state design pattern simply says that an object can change its behavior based on an internal state. Okay, so you can think about it as a state machine that has a certain number of states. Okay, so at any point, a program will have a certain number of states that it can be in, and there is a sequence of how to go from one state to another. Okay, so that's the main idea behind the state pattern. We have a program that can only be in a finite number of states, and we define the rules of how to go from one state to another. And the state can be encapsulated in an object. Okay, so the state can simply be a placeholder, right? So it defines the state but doesn't provide any functionality to it, or it can have functionality attached. Okay, so the state can provide some functionality as well if required, but that's not really necessary. As long as the program knows it's in a certain state, it can simply be a string, or it can be an object, or it can be whatever you want it to be. Okay, so the quick example here is you can think about a blog, an online blog that has certain articles, right? So the articles can be defined in a very superficial way to be in 3 states. One is the draft, okay, when you are simply writing the article. Then we have moderation, where the article is under review and it can be moved back to draft, or it can proceed further to being published, okay? And once it's published, we can think about an expiration date that can send the article back to draft. So these are the 3 states that are available to our article. Of course, in real life, you will have more complex functionality here, but in our simple example, it helps to understand the concept of a state machine. Okay, so let's go ahead in our studio and let's create a new file. I'm going to call this state. Okay, and here what I'd like to define is a simple system that has 2 states, one that is authorized and one that is unauthorized. Okay, so you can have a logged in user or a logged out user. Okay, so let's put this into practice here. So let's create a sealed class state, or let's call this authorization state. Okay, and then we have an object unauthorized, which is an authorization state. Okay, so this is an object, it's a singleton. So we can also have here a class that extends from authorization state. So I'm going to call this authorized. And here we're going to have val username of type string, and it extends from authorization state. So you can see that the state, as long as it's a subset of a certain class, or you can define an interface, you can have either an object, which is a singleton class, or a regular class, right? So I've added both here for completeness. Okay, so I'm going to create a class authorization presenter. Okay, and here let's go ahead and define a private var state, which is a type of authorization state, and by default it's going to be unauthorized. Okay, so we have unauthorized by default. Let's create a val is authorized. That is a Boolean, and let's define the getter here. And the getter is going to simply be when state is authorized, then we get true, and is unauthorized, we get false. Okay, so that is basically our is authorized Boolean. Okay, we define this in the getter. We define the value in the getter based on the state. Okay, so here we have val username of type string. Let's define the getter as well. So we will return when val state equals this dot state. So is authorized, then we get state.username. Is unauthorized, we get something by default, unknown. Okay, so this is our username. And then let's have a function login user. Here we have our username of type string. So our state simply goes to authorized of username. Okay, so that is our login user. Now we also have a fun logout user. Okay, we get no parameters here. We simply return the state to unauthorized. Okay, and let's override the toString function so that we can print out some message here. And I'm going to say equals user $username is logged in. And here we have is authorized. Okay, so user username is logged in, true or false. Okay, so that is our state machine. So you can see basically we have an authorization presenter, that has a state. Okay, and depending on this state, it can be either authorized and unauthorized. And this is the state machine in our particular example. So let's define a class state test. A test method, fun test state. Here, we're going to have a val authorization presenter. Okay, instantiate that. Okay, we're going to have authorization presenter dot login user. Let's call this admin. Okay. Print line authorization presenter, then assertions dot assert that authorization presenter dot is authorized is equal to true. Okay, so we're expecting it to be authorized now. And we need to check the username as well. So assertions dot assert that authorization presenter dot username or what do we call it? Yes, username is equal to admin. Okay, so we have that. Now let's try to log out the user. So authorization presenter dot logout user. And then we will do the same thing here, but change the values. Okay, so here we have false, so is not authorized, and the username is going to be, what did we say it was? Unknown. Okay, let me just print out this here as well. Okay, so let's go ahead and run our code and check out the two states of our finite state machine. Okay, there we go. So user admin is logged in true, user unknown is logged in false. Okay, that really depends on the message that we print here. And then we have our tests that have passed. Okay, so this is a very simple example. Our state machine only has two states, but obviously you can provide a more complex algorithm that really is suited for what you are looking for. Okay, but this is the basic of what a state design pattern is. Okay, so this is the visitor design pattern. So the main idea here is that we try to have a separation between an algorithm and the objects that they operate on. Okay, so the functionality is separate from the from where the functionality is applied. Okay, so here we have two main concepts. We have the visitor and the element, okay, also sometimes called the visitable. So the element accepts any object of type visitor, okay? So obviously visitor and element are going to be interfaces or an abstract class or some sort of establish some sort of hierarchy, right? So the implementations will allow different types of elements here. So the elements accept visitor type objects, and the visitors perform the operation on the element object. So this is a bit tricky to explain, to make you understand just from a theoretical point of view. So it's slightly easier if we have a look at some code, okay, some code examples. So let's go ahead and create a new file here, and I'm going to call this visitor. Okay, so here let's go ahead and define an interface. Report element. All right, so the main idea behind this program is we're going to have a project management system. Okay, so we're going to have various contracts that have some cost per a certain period of time, either month or year or other various types that we can implement. And then we have the visitors that are associated with those particular reports. Okay, so for instance, we have monthly report visitor or yearly report visitor. Okay, and we make the connection between the two in that way. So first of all, we have the interface fun. We're going to take a generic type R, and we're going to say accept. Remember, the elements can accept visitors. And here we're going to have visitor of type report visitor that we're just going to define in a second. That takes a type R and returns us a type R. Okay, and let's define the interface report visitor that has the R here as well. And we're going to mark this with the out keyword because we're just going to return that. So here we have a few functions. So fun visit and a contract of type. Here the problem is we need to first define the contract. So let's pause that for now and let's define the contracts that we're going to have. So class fixed price contract that takes a value cost per year. of type long, and this is a type of report element. Okay, override fun r accept. Okay, so we need to override that, and here we're just going to return visitor.visit this. Okay, so this is one contract. Keep in mind that this will give us an error until we define the reports here. All right, so next contract is going to be time and materials contract, val cost per hour, also of type long, and this one takes val hours of type long as well, and returns is a type of report element. Override our function, and here we will also return visitor.visit this. Okay, easy enough. And then we have our third type of contract, which is a support contract, val cost per month, which is a type long, also a report element. And here we have the same structure. We have our visitor.visit this type of contract. Okay, so now we're ready to define our report visitor based on the contracts that we have here. So the contract is going to be, the first one is going to be a fixed price contract, and will return an R. Fun visit contract of type time and material contract. Okay, returning an R, and fun visit contract, and this is going to be a type of support contract, also returning an R. Okay, so now the visitors that we define have to implement these three visit functions, okay, based on the contracts that we have available. Okay, so now let's instantiate those. So class monthly cost report visitor is a type of report visitor, and the type here is going to be long. Okay, so let's go ahead and implement all the members. So the first one, the fixed price contract, okay, so that is a monthly cost, so that is going to be contract dot cost per year divided by 12. Okay, now for the time and materials, we're gonna have contract dot cost per hour times contract dot hours. Okay, so we're calculating basically the cost based on the type of contract that we have, and we get cost per hour times hours. And then finally, the last one, the support contract, is going to simply be contract dot cost per month. Okay, so that is our monthly cost report visitor. Then we have our yearly report visitor. Is going to also be a report visitor that gives us a type long as an out type. And here, of course, we're going to implement these members. So for the first one, we have fixed price contract. This is already per year, so we can simply return contract dot cost per year. Okay, keep in mind that this is a yearly report. Then here, time and material, we're going to have contract dot cost per hour times contract dot hours. Okay, so the same amount. And then finally, for the support contract, we're going to have contract dot cost per month times 12. Okay, yearly is times cost per month times 12. Okay, so these are our reports, and these are our contracts. Okay, so the contracts are our elements, and then the reports are our visitors. Okay, easy enough. Now, let's go ahead and create our test class. So class visitor test at test fun test visitor. Okay, so here let's go ahead and define our project. So let's say val project alpha is going to be a fixed price contract of cost per year is going to be 10,000. Okay, so val project beta is going to be a support contract, which has a cost per month of, let's say, 500. Val project gamma is time and materials contract. Not that, time and materials contract. That is going to be for the hours. Let's say we have 150 hours, and for the 10 hours, so cost 150 per 10 hours. And then let me do gamma here, and I'm going to duplicate that project kappa, and that's going to be 50 hours and 50 cost per hour and 50 hours. Okay, so these are our 4 projects. So let's add them to an array. So val projects array list of project alpha, project beta, gamma, and kappa. Okay, now val monthly cost visitor is going to be an instance of monthly cost report visitor. Val monthly cost will be projects dot map. That's project dot map. So here we have it dot accept our visitor. So the visitor is going to be our monthly cost visitor. And finally, we're going to do dot sum, and we get the monthly cost. Okay, now print line monthly cost is going to be our value. And then let's assert. So assertions dot assert that monthly cost dot is equal to, I've made this calculation before, 5333. Okay, so now we have our monthly cost, but let's create a yearly visitor as well. So yearly cost visitor is going to be yearly cost report, yearly report visitor. I should have probably named this yearly cost report. Let me refactor that. Rename yearly cost. Okay, so I have my yearly cost report visitor. Then val yearly cost is going to be project dot map it dot accept my yearly cost visitor dot sum. Okay, finally we're going to print line my yearly cost is going to be my yearly cost value. And then finally assertions dot assert that my yearly cost is equal to 20,000. Okay, so if my calculations are correct, then we should get correct values here for the tests, and then we're gonna get the printouts as well. So let's go ahead and run our code. There we go. So we have our monthly cost 5333 and our yearly cost 20,000. Okay, so basically you can see the design pattern in place here. We have our contracts that are basically report elements. Okay, we define this element interface that allows our visitors, that accept our visitors. Okay, and this simply calls this method. So the algorithm to calculate the functionality is here in the methods. Okay, here we are simply calling visitor.visit because this is designed to accept the visitor types. Okay, and here we can define as many visitor types as we want, and we can extend this functionality with monthly cost, yearly cost. We can have daily cost or things like that, whatever makes sense for your particular project. Okay, so hope that makes it clear. That is the visitor design pattern. All right, so the mediator design pattern. The mediator design pattern is basically a central object that is used for communicating between objects. Okay, so you can think about it as a client-server architecture where the clients, there are multiple clients that communicate with a central repository, a central server. Okay, so the objects don't talk to each other. They always talk to a mediator. And the main idea here is that we reduce the dependencies between objects. Okay, the objects or the clients don't need to know about each other. They really only care about knowing the existence of the mediator. And once that is established, then they don't really care about communicating directly with other objects. So the classical example here is a chat application. Okay, so you might have a chat where you have a few different clients and the clients can talk to each other directly. Okay, so obviously this is an unsustainable architecture. You cannot really build a system like that, especially when you grow the number of clients and the number of connections between the clients. So what you need is a central location, a central point, a mediator where the clients communicate with the mediator and the mediator sends the information down the chain to the clients. Okay, so a central repository of some sort. A very, very useful pattern that is applicable in many instances. So let's go ahead and create our own very simple chat application, or I should say broadcasting application rather. So let's go ahead and create a new file. I'm going to call this mediator. Okay, and the first one I'm going to define is going to be the class chat user. Okay, so this has a private val mediator, which is going to be a chat mediator. Okay, I'm going to define that in a second. And then I'm going to have a private val name of type string. Okay, so I have two functions. One is to send a message of type string. So the mediator, we're going to print line first of all, $name sending message $message. Okay, and then we're going to have mediator dot send message of MSG. Okay, we're going to define this function as well. So that is one function, and then we have receive a message of type string. And here we're simply going to print line name receiving or received message $MSG. Okay, so send and receive, very, very basic functionality. Now let's define a class mediator. We don't need any parameters for this one, so I'm going to have a private val users. That's going to be an array list of. And here I'm going to have chat users. Okay, now we have a fun send message, MSG of type string, and we have our user of type chat user. Okay, so this is the user that has sent the message basically. Okay, so we don't want to send that message that we received to the same chat user. So we're going to have users.filter for it is not equal to user dot for each, and we're going to have it dot receive message. That's pretty much all there is to it. Right, so we can put this on a new line here so that it looks a bit better. Okay, so we have our send message function, and then we have our add user function, user of type chat user. This one returns a chat mediator so that we can, no, it's just a mediator, so that we can chain these operations together. And here we have apply users dot add my user. Okay, so we have apply. Oh, right, we need the equal sign, so we're just returning the result from the apply function. Okay, so we have the mediator, and now I'm going to create the mediator test class. We don't need that. All right, so a test function, fun test mediator. Okay, so let's go ahead and first create our mediator. Okay, then we're going to create, let's say, 3 users. Alice is going to be chat user of mediator and Alice. I'm going to duplicate that. Second one is Bob and the name Bob. Alice, Bob, and let's say Carol. Carol. Okay, so we have our mediator, we have our 3 users. Let's add our users to the mediator. So mediator dot add user Alice dot add user Bob dot add user Carol. Okay, so our users are added to the mediator, and then let's send a message. Carol dot send hi, under quotes, hi everyone. All right, let's go ahead and run our code. And what should happen here is basically, I am missing something. Okay, it's not a chat mediator, it's a simple mediator. And here I am sending message, and I need the user as well. Okay, so the user is going to be this. Okay, all good. Let's go ahead and run the code. There we go. So basically what happens here, Carol is sending the message, Alice is receiving the message, and Bob is receiving the message. And obviously Carol is not receiving the same message that it's sent. Okay, there's no real point to that. Okay, so that is the mediator. Now, of course, Alice, Bob, and Carol don't really know about each other. All that Carol knows when they're sending a message is they are contacting the mediator, okay, through their send functionality. Okay, they don't know who's going to receive that message. So that's why I said this is not really a chat, but more of a broadcast system. But a chat is a nice way easy way to conceptualize this. So this is the mediator pattern. It's basically a central repository that performs some functionality that multiple other elements require, and then they contact that central functionality store for whatever they need to do. Okay, so the memento design pattern. A memento is basically a way to store some information. Okay, so that's what the design pattern does. The design pattern basically allows us to save and restore previous state of an object or a piece of functionality, okay, part of your code, without revealing implementation details. Okay, so we want to have a actor, a client, or whatever part of your code does that. We have a component that decides when a state would be saved and when a state is restored, but that actor doesn't really care about how that state is saved and restored. Okay, it only cares about when and making the decision to do that. So here we have 3 components of the memento design pattern. First is the memento itself, which is an object that stores the state. Okay, then we have the originator, which creates the state. Okay, it allows us to, it's basically the object that contains information about how to store the state and what information goes into the state. and then the caretaker, which decides to save and restore. This is the one that makes the decision, and you could say that is the user of the application, or it can be an internal part of your program that is designed to do that. Okay, so a quick example would be a text editor, right? Where we have at each point we want to be able to have an undo command that returns to our previous state. So that means the originator, which is the editor, will create mementos as it goes through the editing process. And when the user clicks on that undo button, then the caretaker is activated and restores a previous state. Okay, that is a quick example. Let's go to our editor and put this into a program. So I'm going to call this memento. So first of all, let's define a data class memento that has a val state of type string. Okay, we're going to make it simple. Our state in our small example program is a string. And now we're going to define our class originator var state of type string, fun create memento. This returns us a memento data class, and here we're going to simply return memento of state. Okay, and then we have fun restore memento, which simply says state. This needs to be passed a memento here, and state is going to be memento dot state. Okay, so we are basically restoring the state from the memento that we have. All right, so next up we have a class caretaker that has a private val memento list that is an array list of mementos. Okay, we have a function save state, and the state is going to be of type memento. So we're saving this, so memento list dot add our state, and then finally we have our restore. And here we can take an index, for example, of type int that returns us a memento. Okay, so we have a list of mementos, so we can access any memento in that list based on the index. So here we are simply returning memento list of index. Okay, I like to simplify my code where I can. All right, so we don't need the return keyword, even better. There we go. All that is pretty good. Let's go ahead and create our test class. So memento test at test fun test memento. So let's go ahead and create our originator. Is going to be an originator of initial state. Okay, so we're defining an originator with an initial state, and we're defining a caretaker as well. Okay, now we're going to say caretaker dot save state. Okay, so the originator at this point has a certain state. We want to save that state, and we need to pass it here. So originator dot create memento. Okay, so the originator creates the memento, and the caretaker saves that memento in its own memento list. Now let's update. Originator.state is going to be state 1. Okay, then caretaker dot save state originator dot create memento. Okay. Let's update that again so that we can test later on various restores. Okay, so originator.state is going to be state 2, and we're going to save the state again. Okay, so we have 3 states at the moment. Okay, so let's go ahead and print line current state is dollar originator dot state. Okay, so we have printed that. So let's go ahead and create some assertions. So assertions, let's use the assert J1, assert that originator dot state is equal to, so at the moment the state should be state 2. Okay, then we're going to say originator dot restore memento, and here we have caretaker dot restore index 1, let's say. So the index 1 would be state 1. This is 0, 1, and 2. Okay, we're going to assert, there's a space required here. We're going to assert that the current state is state 1. And then I'm going to do the same thing, originator.restore memento, caretaker.restore 0. Paste that again, and this is going to be initial state. And we can even go forward. So we have an undo button and we have a redo button. So originator.restore memento, caretaker.restore 2, and this should be state 2. Okay, so we basically go undo once, undo twice, and then redo 2 times so that we get to the last value that we had. So let's go ahead and run the code. Okay, so we get all of our tests were completed successfully. I only get a current state here because I'm only printing it here, but let's go ahead and print it in a few more places. Okay, so let's print it here, and let's print it here after the restore, after all the restores. Okay, so let me run this again. We should see a lot more output now. There we go. So initial state, state 1, 2, back to 1, back to initial, and then we're jumping all the way to the last state here. So you can see basically this is a kind of a memory system where we remember the states that a certain class originator was in, okay? And we can jump back and forth. You can add a bit more complexity to this so that we can say when we are at state, let's say state 0 that we were here, and we create another state, okay, the way we did here, save state, it overrides the following states, okay, so that we don't add it to the end of our list. So that is a more complete undo, redo system, but in its most basic form, and to symbolize, to show you how the memento design pattern works, I think this is a really good way because it shows us how we can maintain a list of states without worrying too much on the internal mechanism of the originator, okay? The caretaker only cares about the actual memento state and not on the internal functionality of the originator object. Okay, so that, I hope that's clear. That is the memento design pattern. All right, so we have reached the end of this course. I really hope you found it useful and interesting, okay? I hope you took a lot of information from it, and I really do hope you apply this knowledge that you learned here in your everyday programming, okay? A good programmer that uses a lot of design patterns is very, very noticeable when I look at a piece of code and see how they structure the code. It's very obvious if they followed a certain architecture or not. So first of all, I want to say a big thank you for taking this course. I hope you've enjoyed it. I hope you found it useful, and I hope you apply the knowledge in your everyday life, and hope to see you again soon. I have a ton of courses on various topics here on Udemy, and I do hope you have a look at those. And if you find something that looks interesting, have a look at that as well. So thank you again, and I will see you again soon.